All right, let's see. I'm hoping the stream works a bit better today than it usually does. I tried to set OBS settings to like do adaptive bitrate things, so we'll see if that's a bad idea or a good idea. Keyboard sounds. Keyboard sounds are not planned today. I mean, if we really need to, we can do keyboard sounds. Maybe this is as much keyboard as we will hear today. Looks like the stream is working, which is good. I was working on some small things today in the morning. There's nothing really interesting going on here, so yeah, like we don't, there's not gonna be any code probably that is written on stream today, but you know, we'll see how it goes. The point of the stream, we have 4 minutes before we officially start. So technically we're starting in 4 minutes. But the point of the stream is to just talk about stuff. Talk about whatever you guys want to talk about. I have some backup things, sort of, like if there's no interesting questions or anything like this, then I can talk about some things I wanted to talk about, but usually the way these things go is, you know, we have questions and it takes me time to answer questions and to talk about stuff, and, you know, time goes by pretty quickly. So topics for today are pretty free, but really they include, you know, like, I'm happy to talk about things that I find interesting. Things that I find interesting are around technology specifically are things like graphics. Okay, let me. Things like performance in really a wide set of areas. So it's just general optimizations, algorithms, CMD, multi-threading, all of that. I worked a bunch with compression recently. I am by no means an expert in compression, but I feel like I know enough to try to pretend that I know something, which, you know, could be good enough. I've spent many years really kind of doing some programming language stuff in my spare time, but in the last year or so I've been doing a lot of programming language stuff at work. So we can talk about languages, you know, parsers, compilers, interpreters, VMs, JIT, and all of that stuff, all of the fun things that come out of this. What else? I don't know. We can talk about some web stuff, although a lot of the web stuff that I'm doing is around graphics or performance, so it's really a subset of this. But yeah, we can talk about WebAssembly. And whatever you guys want to talk about in general. So since it's 9:59, we might as well start. And yeah, so like the way it's gonna go is you guys should just ask questions in chat on whatever you guys are curious about, or things that might be interesting to talk about, and then we can just have a slightly one-sided discussion, and then we'll see how it goes. What type of keys are those? So this is Cherry MX Blue, and it's DAS keyboard. Basically, the way this happened is my old keyboard died again, and I think my keyboard dies every 3 to 4 months or something. I don't particularly take good care of it, but it kind of got old. All right. I don't know if this stream will work well today, but whatever. This thing's usually, YouTube often, for some reason, says that the quality is poor, but when I look at the recording later, at least the recording's fine. So, my keyboard died again, and I'm like, I might as well just get a good keyboard, like not a keyboard that costs like $30, but a keyboard that costs like $100 or whatever. And I've never really tried mechanical keyboards. And I just decided to get a random mechanical keyboard, and it was Das Keyboard. Das Keyboard kind of popped up. I am usually relatively sensitive to the sound, like I don't like loud clicks, so I got a Cherry Max Blue. I've been really happy with this so far. However, I'm now worried that when this whole quarantine situation resolves itself, and everybody goes back to work, I'll have to use a mechanical keyboard because I'm kind of digging this, and people around me in the office will be upset. But it's not my problem, it's their problem, so it's fine. Do I have a Shader Toy account? I do have a Shader Toy account. There's nothing interesting on it. In fact, I want to say I created a Shader Toy account like I'm not even signed in. I feel like I've created a Shader Toy account just now, and it was because I needed to upload one shader to show that there was like a discussion around hash functions, and and the hash function, there's like good hash functions and bad hash functions, and there's this classically used hash function which is called Wong hash. Is for mapping integers to integers, and it's really not that good in some cases. I'm sure video compression will not really work with this, but if you assuming video compression actually worked, I'm also downsampling my stream to 1080p, I believe, so probably it will not work, but there's really obvious patterns in this specific case, and Wong hash is kind of prone to having more common patterns in some cases, and my go-to hash for integers is usually murmur hash, or rather there is like this general purpose hashing algorithm which is called murmur 3, and it has at the very end of the hash, it has this finalizer that scrambles bits around, and basically anytime I now need an integer to integer hash, I just go for this because it has good distribution. My shader toy, I have to press the run button. Like in this case, you don't really see these patterns, and it's just really good hash. It's fast, it's simple, it takes like 3 lines of code, so 5 lines of code, so just copy and paste it wherever you go, and anyway, so I do have a shader toy account, but there's nothing interesting on my shader toy account. Challenges porting Roblox to Androids. I'm gonna talk a bit about this. It's a large topic, so let me look at the other things. What kind of job allows you to work on programming languages? So I work at Roblox. I worked at Roblox for the last many years, and Roblox uses Lua as a programming language of choice. And for many years, we have just treated Lua as a black box, more or less. Like, we fix bugs in it occasionally whenever they come up, but it's basically, here's Lua, here's what it can do, here's how it's implemented, just do what you want with this. And through a series of, there's like a sequence of events that led to this, which is kind of, I can talk about this. Like, the way this happened is, so the way this happened is, right, so there was Lua, and there was Lua 5.1. And we've used it for years. And then at some point, a few years ago, I wrote a static analyzer. It's basically similar to Lua check, but it didn't really use Lua check. Lua check isn't very fast, and it's all written in Lua, which is sort of good, but also sort of bad. And we kind of needed something that can really quickly give the kinds of warnings that Lua check might be able to give you, but our so it's a static analyzer, or it's like a linting tool, right? But it was a bit less opinionated, I would say, than Lua check, because the goal was to just the goal was to help people find errors in their code, not as much create a common style or anything like this. And so because of this, I had to write a really, really fast parser for Lua. And the parser, unlike Lua 5.1, the parser produced an AST. And so then we started talking about adding types to Lua, or by types I mean specifically adding static or gradual typing, it's called. So you can do type annotations in your Lua code, and if you look at what happened in JavaScript, it's kind of the same story, where there's a lot of code that people write in JavaScript, and at some point it just became unsustainable to maintain these code bases. And so then Microsoft came up with TypeScript, right? And then Facebook came up with Flow, and so now TypeScript, in my impression, is TypeScript wins in terms of the kind of community adoption by like leaps and bounds. So, but anyway, effectively there's now two type dialects of JavaScript. And so we kind of said, well, we kind of need to do the same, because at this point we had something like 400,000 lines of Lua code that we write and maintain. And God knows how many, millions, tens of millions, hundreds of millions lines of code that the community maintains. So I did a Hackweek project on this a couple of years ago, where in a week I was like, hey, what can you do in a week to convince people that it's a great idea? And so people were sufficiently convinced. And so then we started writing the type checker framework that's based on the same parser and ST, but then you add type inference and, actual checker. And this is like really hard. I can talk about some problems with this at some point, but it's really, really hard because your job is to model the language runtime semantics to a sufficient degree to be able to find 90% of errors that you might see at runtime, to be able to find them at compile time. And it's like really, really hard to do that, because there is this constant balance between accuracy of your type information versus, how do I put this? Like if there is an escape hatch always where you can say the type checker doesn't know what X is, but then the problem is if you have bugs around the use of X, then the type checker is less useful, right? But conversely, if you are modeling X too strictly, like if at runtime you can do more things with X than the type checker knows, then you're prohibiting some technically valid types of programs. And so this is a complex balance. And then at the end of 2018, we were discussing performance and kind of what to do about this. And I wrote a plan for like a tech spec for this, and then implemented most of this, which is that now there's also a compiler that produces bytecode and interpreter that is like really fast. It's competitive with Lua JIT interpreter. It's much faster than Lua. And also on Hackweek last year, or like basically a few months ago, I also did a JIT prototype, and we're now thinking about how to kind of deploy this stuff. So effectively, because we have so much code that we write in Lua, and because our community has so much code that they write in Lua, it makes a lot of sense for us to invest in this whole like ecosystem. And the thing is, historically we ended up with Lua for better or for worse. If we ended up with JavaScript like 10 years ago, 15 years ago, right, a lot of this would have been done by other people. But effectively we are doing today what other companies have done in the web space over the last like 5 years or so. All right, let me actually go through the list now properly. I guess I sort of skipped. So there's a bunch of questions that are queuing up, so I will try to be relatively contained in how much time I spent discussing them. So challenges porting Roblox to Android. Oh my god. I mean, this is not a very happy topic, but fine, we can talk about this. So Android is an interesting system. Android is insanely big for us right now. I don't think I can quote the specific like market share or whatever, but it's huge. For years and years, Roblox was this platform where, you know, desktop is the biggest one, and then mobile is this like tiny sliver, and then mobile grew and grew and grew, and now it's really crazy how big mobile is for us, and specifically how big Android is. iOS is also big, but just not as big. And so there's a ton, like it's a really important platform for us. However, there is many problems with Android. So problem number one is there is this terrible fragmentation of hardware, software, and in both hardware and software there is multiple layers of this, right? And like, so the person who's asking this question, I'm pretty sure knows about all of this, but just for the benefit of other people. So let's talk about hardware for a second. Thankfully for us, there's a dominant CPU architecture, which is ARM. We actually don't build our game for any other architectures, although curiously, you can play Roblox on Chromebook with an Intel CPU using an emulation library that Google just kind of implements and maintains. I always forget how it's called, but it basically does dynamic recompilation of ARM code, or maybe static, in x86 code, and there's like bugs in that occasionally and stuff like that. But so there's one more or less CPU architecture. There's ARM. There's sort of two variants, 32 and 64. There is several CPU vendors, but we don't have, like, the behavior of the CPU is the same, the performance is different, right? On the GPU side, it's kind of a mess. So there is three major vendors, two really major vendors, ARM and Qualcomm, on the GPU side. There is PowerVR, which is smaller than these two, but it's like reasonably big. And also there's other weird vendors, you know, like if you look at, with a really large user base, it's kind of important for us to care about small percentages of this user base. It's like 1% of the users for us is actually a lot of people. So there's Broadcom, and there was some other, I forget. There was some other fifth one that I remember. Oh right, sorry, I forgot. There is also NVIDIA, of course. NVIDIA makes Tegra chips, and you can buy a Chrome Pixelbook or whatever it's called with Tegra. So yeah, there was some other one. Then for each vendor, there's many versions. There's like years of versions of graphics drivers, and so graphics is like the biggest problem on Android by far, because then you have GLES2, then you have GLES3, and you would think, oh, I will always target GLES2, but for us it's actually important to target GLES3 because for performance reasons we need to use some features on 3 that are not available on 2. And now, of course, there is the, you know, the darling API of many, Vulkan, which is really good for performance. Like, it's dramatically faster. The GLS driver for all of these vendors aren't that great. The Vulkan drivers are also not that great in terms of robustness, but they're like really good, much better, let me put it this way. Not really good, but much better in terms of performance. So if your ultimate goal is performance, which it is for us, like Vulkan is important. But so then you can look at like the these factors multiply, right? So there's 5 GPU vendors, like 3 major ones, you know, 2 minor ones, let's say, or 2 major ones, 3 minor ones, however you want to count like 3 graphics APIs that we support, and then years of driver versions. All right, so like there's just a large possibility space. Then, to add an insult to injury, there's 2 more things that are true of this ecosystem. So one is conformance testing, is bad. Conformance testing means when a manufacturer ships a device, or when like a graphics vendor ships a driver or whatever, they have a battery of tests that they run to ask, hey, does this GLES implementation actually implement GLES, right? And so there's a battery of tests. However, this battery of tests isn't really very adequate in either of these APIs, really, because it doesn't, like, you would hope that if this battery of tests works, then the application would work. Like, basically any decently complex application would work, even if it maybe is slow, right? Slow is fine, but at least it would work. Fortunately, this is not really the case. There is a really large gaps in conformance. Plus, I will run out of colors at some point. I feel like I already have. I'm not sure what is this. Okay. So plus there is the whole problem, which is how do I put this? Like, nobody knows. Wow, this is really funky. Which version runs where? So you talk to a graphics vendor and you're like, hey, I have this problem in your driver. And they're like, yeah, not a problem at all. Our driver version 2.7 fixed this. And you're like, okay, when do you think you can ship this? And then you realize that the graphics vendors on Android don't ship drivers. The entity that ships drivers is, I guess, the like the combination of the phone manufacturer and the cellular service provider. Somehow they decide whether to roll an update to existing devices. And so it's not Google, it's not the actual like company that builds the devices, and it's often not even just the phone manufacturer. So like there's a really long chain, nobody knows what software exists where, and this results in a crazy fragmentation in the ecosystem, right? So a lot of time we spend on Android to this day on all of the APIs really is just making sure like the game renders properly. Every single graphics change that we ship comes behind a set of flags that we can at a moment's notice like disable or enable, because it's just unsustainable to just ship an update without kind of ability to immediately disable portions of the code. So that's a big problem. The other big problem, okay, I'm gonna spend like 5 or 10 more minutes like ranting about this, and then we'll stop, but I feel like I could go for hours. So the other really big problem is, so okay, fine, like there's a lot of fragmentation, cool. So the next big problem is that I feel like the whole Android ecosystem started being semi-serious about games like, you know, a couple of years ago, or even not really. And by games, so games is an amorphous concept, but like it used to be the case that you would report bugs in the native development kit to Google, and they would be genuinely surprised that you're not using Java to program your games. This was like a number of years ago, but it kind of shows in the quality of the tooling that exists there. So the tools, and by tools I specifically mean things like performance profiling, oh my god, I can't write today, sorry. Maybe I should type and you'll hear the beautiful sounds. Debugging, deployment, version management, surprisingly, crash reporting. Deployment would specifically be in local workflows, like you are trying to run the code on device. Crash reporting is like you shipped your code, how does it work? All of these for native code. I don't know much about Java because I don't really care too much about the Java, the state of Java ecosystem there. But all of these were consistently in really bad shape. throughout our development process. They're getting better. Debugging has worked for the last couple of years. It has not worked for the years before that. Deployment continues to be kind of bad. There's this crazy combination. I'm sure some of this is our fault, but there's this crazy combination of like Gradle and ADB and I don't even know, like Maven, like don't get me started. Profiling. So CPU profiler that is in Android Studio, I think we were able to run it like with reasonable success either this year or late last year for the first time, which just blows my mind. How do these things happen? GPU, let's not talk about this. Crash reporting, like effectively we had to not quite build our own solution, like integrate somebody else's solution, but so all of these things are really bad there, right? And by itself, if either like if you have fragmentation but you have really fantastic tools and fantastic kind of if Google was seriously committed to making native development of Android awesome for the last 5 years, I feel like today we would be in an awesome shape. But I just don't know that they are. I'm sure there is small teams at Google that are committed and things are getting better, but it's kind of too little too late. Like for us it's sustained pains over many years. By the way, what I'm saying on the stream is not an official Roblox position, but I kind of hate all of this. Yeah, so by itself, like if either side is a problem, you can sort of deal with this. Like on PC, there is a really crazily fragmented market, but on PC there is not as big of a problem with the deployment of software on customers' computers. It's still a problem in some areas, but the tools are so much better, etc., etc. And also I just feel like the stability of software in general, of like the software stack in general on Android is just not very good. And there are things that are still true around performance specifically that still boggle my mind. Like there's crazy problems with multi-threading that we are starting to look into that again are just like the thread scheduler on Android has really bad latency for reasons that are not quite clear. The clock frequency adjustment is really broken on so many devices. Like you look at you look at an iPhone. So I've used an iPhone for the last many years, and Android keeps getting better, but it's just I feel like I have PTSD from Android in the sense that like it's going to be hard for me to ever use an Android device as my personal device because so like the clock frequency scaling based on temperature continues to be pretty bad on many devices. Scheduler is bad. There's this whole big little craziness where many devices now ship with octa cores, where you have 8 cores. 4 of them are fast, 4 of them are slow. You never know which core your code is running on. Never. There's no API for there's nothing. Anyway, so it's bad. I hope this answers the question in detail, but it's pretty bad. Now, we manage, right? So we have a team that works on this. We don't have a specific Android team, but it's kind of everybody on the team knows how to work with Android, knows about a lot of this stuff. We work a lot on our code to make it more resilient to things like this. We build our own tools, we have our own profiler that we use most of the time. We integrated crash reporting. We deal with the lack of good version management through flag switching through the web configuration, stuff like that. So we kind of cope, right? It's not a pleasant experience. For example, when we shipped Metal on iOS, the way this happened is I think I spent a Friday. It was a long Friday, but it was a Friday building a prototype, and it was way faster. And we were awesome, let's just go for it. And then we finished the code, real production code, in a few weeks. I forget, a month. And then we shipped it in a month. And on Android, it took us a year or more to ship Vulkan. So yeah. Anyway, It's kind of sad. Things keep getting better though. Like I feel like in 10 years, this would be a horror story that you tell to your children or grandchildren or whatever. But right now, it's just the messy reality of the situation. Yeah, I mean, okay, we can talk about this. I don't think it's about not knowing how the scheduler works. I think it's about the scheduler. So the specific thing is, for example, you wake up a thread, and the latency of the thread wake up is just way larger than on any other operating system. But anyway, so thoughts on render graphs as a way to solve having to handle manual welcome transition stuff. So I'm kind of a split opinion on render graphs. I generally like the idea of render graphs, but I think a lot of people seem to take it too far. So, how do I explain this concisely? So there is the core problem that render graphs solve, which is a valuable problem to solve. You don't have to solve it the way render graphs do. We don't have render graph. We have different ways to deal with this whole time travel problem that work fine on reasonably simple mobile-friendly renders. They probably don't work well for like Frostbite or whatever. I talked about this on my reboot develop red talk from last year. But so does the basic problem that actually there's two basic problems that render graphs solve that are valuable problems to solve. Render graphs are not the only way to solve them, but they are a reasonable way to solve them. So one is future and past, in some cases, uses of a resource. Like knowing this is important to set up barriers well. The other thing that render graphs are good at is dealing with the lifetime of transient resources. Meaning you have a render target that you render to, and then you read from this render target in a few passes in your frame. And then you don't need the memory that that render target occupies for more than that duration of time, right? And so you could share that memory with other resources. Now, render graphs aren't actually necessary to solve this problem at all. In the last several companies I worked at, including Roblox, like there were solutions for this problem that didn't require render graph, right? But render graph are a tool to solve this, and this is a valuable problem to solve, right? My dissatisfaction with render graph comes from two places. So one is just in general, so there are a lot of people who are fan of declarative programming, and declarative programming is like neat, but there's many practical problems with it, and render graphs kind of inherit parts of this. So like, for example, what if you have some code, some rendering code that doesn't have to run every frame, or that is conditional based on the user's configuration? If you're running imperative code, if you're writing imperative code, it's like, oh, hey, okay, if this condition is false, I'm not going to do that. Super simple. If your style of programming is declarative, suddenly it's either the case that you have to have two versions of the program, right? So in render graph context, this would be, okay, whenever like a user setting switches, we create a new render graph. Or maybe we have two render graphs. One is used to render our frame, and one is used to render our like minimap that doesn't happen every frame. And there are some dependencies between the render graphs that are set up somehow. Or you have to embed the extra facilities into your render graph to handle conditionals. like, oh, this node is actually conditional based on this runtime value. And this makes your random graph system more complicated. So there's many things that are really beautifully simple in imperative code, but really hard, like much harder in declarative code. Of course, it's true, like the reverse is true as well, right? There are things that are really easy in declarative code, which is this whole like look into the future to figure out where this thing is going to be used, if it's going to be used at all. That's hard. So, but yes, my my kind of grumbles with random graphs are, so they're kind of complicated. Dynamic structure is hard. And like all of these things are solvable, right? It's just that like if you don't have to solve, like I like not solving problems that I don't need to solve. So having to solve these problems is not always great. Fundamentally, oops, hold on. So fundamentally, render graphs are a framework that enforces constraints on your code. Historically, basically every framework that I've ever used was bad. It was bad because the constraints that it imposed on you didn't actually optimally map to the problem at hand for any given problem. And so it made some things really beautifully simple to solve, but it enforced a large burden on you, and some things it made very hard to solve. So that's just like a general thing. The big thing that I don't like about render graphs is that people who, it's kind of how, it's kind of like, to an extent, like ECS, where it's sort of this religious belief, not religious belief, but like it becomes a bit of an obsession with the thing. So you aren't kind of trying to objectively estimate the merits. You're just taking the framework, render graphs in this case at face value, and try to figure out the ways to just apply this like to all of the problems that you have. So I have one specific thing in mind where there's two things actually where people go overboard with this. One thing is complex to explain, so I'll just leave it as like it makes, you know, some things that are relatively simple relatively complicated. But one thing that people started doing with render graphs is scheduling. It's very hard. So there is this problem in computer graphics where, you know, depending on the order, so first, depending on the order that things happen within your frame, you actually might have different memory impact or different performance profile, because you can reuse more or less resources, or you can share more or less data, or things like that. Like there's classical examples around for what's a good one. There's this canonical thing really, which is in deferred shading. People used to have this style of deferred shading for years and years, where, not years and years, but like it was really common back in the day, where you have one shadow map. And then you have 1,000, well, okay, you don't have 1,000 lights, but you have like 10, 20 lights that cast shadows. And what you do is you render shadows to the shadow map for the light source. Then you render some geometry into your G buffer to use that shadow map to do the first shadows. And then you repeat, right? And so this is nice from the memory consumption perspective. Your memory consumption is static regardless of how many shadow casting lights you have, which is nice. It's actually bad for performance for a variety of reasons. It's really bad for performance on tiling hardware, although differentiating in general is a bit of a mixed blessing there, but it can be bad even on immediate mode. So a lot of more recent differentiating approaches shifted to the mode where you render all of the lights, all of the shadows for all of the lights into a big like atlas or texture array or whatever you want to use, and then you apply them in few passes, not necessarily one, but few passes to your G buffer. And then also there's this recent kind of trend where some GPU architectures can run compute shaders asynchronously with the rest of the graphics pipeline, and so it's tempting to use that. And so I've seen too many people and presentations kind of thrilled with the idea that once you have this render graph, well, it's a graph, so it's a graph that perfectly declares the dependencies, which means that you can determine the order that the graph executes in, and also which execution queues, which compute or graphics or whatever, different stages execute on. It sounds like a really great idea. And then the next problem is, to write a good scheduler, you have to be able to predict performance of the resulting schedule as like a first basic thing, right? Like if you don't know how fast the thing runs, then good luck trying to schedule it optimally. Turns out it's a really hard problem, because turns out like whether you get a gain from async compute or not in a specific situation is really, really complex. Like it's really depends on the context. And also this memory performance balance is really hard to strike well. And so what I've seen happen a few times now is that somebody builds a render graph system, and then they're like, awesome, let's add scheduler to that. And then you add a scheduler to this. And then you can't, like a graphics engineer can't look at the render graph structure and predict how it's going to schedule, right? So that's the first problem. The second problem is the scheduling is suboptimal. So then you add these hints, scheduling hints, to the render graph that says, oh, this node is actually more compute intensive than this node. So, which presumably means, you know, it's more productive to, or like this node is raster bound, so it's perfectly fine to run async compute during that. I'm kind of skeptical that all of this stuff really works well. I feel like in a lot of cases, people are just chasing this dream of a declarative, you know, graph. And this does give you value, but I'm skeptical that it gives you so much value that the downsides are kind of covered by that. So in my view, I think a perfectly reasonable design is to do the simplest random graph possible that doesn't do scheduling for you at all, that just relies on the dependencies back and forth to figure out where to place the barriers. And that I think can work really well. But I just worry that there is this trend of just taking this too far and just applying this in cases where it doesn't belong. And it seems like it's a beautiful, pure structure, but it imposes a structure on you, and it actually makes your code more complicated and it's harder to reason about. And so you have to keep like going back to, oh, this frame runs slow. How do I run this part concurrently with that part? Oh, like the scheduler didn't do this. Let me try to bias the priority here. Oh, it still doesn't work. Let me go debug the scheduler now and see what it's doing. And it's just, it feels like it's too much mental burden for kind of for what it's worth, right? I have a very parallel example from the CPU scheduling work. I've always really liked the idea where the task system that distributes your jobs has really minimal awareness of the dependencies between tasks, and it's possible to do a good job with that. Maybe like I can talk more about this at some point, but I dislike the data flow designs where you build this complex graph of nodes and you build, I forget, there was some 10 years ago, there was some big engine was trying to do this thing, Gamebryo perhaps, where they had this data flow thing where you said this node pipes data into this node, and this buffer is this big, and this can run concurrently with that. And it just felt like, oh my god, there's so much effort kind of trying to make it work, and it doesn't work, and you can't reason about performance well. Like, it could be so much simpler if you didn't do that. So anyway, love-hate relationship with render graphs. Is Lua going to be available as a public library? We're gonna ship a binary with the interpreter and type checker and stuff in a couple of months, I think. No word on open source or anything like this. This stuff is a bit hard to figure out. Uh, Meshlet generation algo. I guess you had the triangle which uses min number of new vertices. How do you resolve tie breaks? The least volume. I use least volume sphere column least cone angle for cone column. So the current algorithm that I have is really dumb. It doesn't do things like that. I am planning to look into this stuff now that I'm done with the compression. One day I want to figure out how to fix this keyframe frequency of 4 seconds or less error. And the current keyframe frequency is 8 seconds, which suspiciously seems like just some hard-coded setting inside OBS that I have to switch for YouTube. Anyway. So, my current algorithm is dumb. I experimented with a couple of different algorithms before, and I'm kind of, I'm not at the point yet where I know a good answer because I haven't like finished this work. I'm planning to do this over the next like month or so, maybe. Time availability pending and stuff like this. But yeah, there's a couple of things that you are trying to balance, right? So one is you're trying to balance just reuse. Reuse of vertices within reuse of vertices between triangles, right? So like the ideal meshlet is the meshlet that has the fewest, like the largest ratio of triangles to unique vertices, right? The second one that you are trying to balance in many cases is spatial locality. Which you could think of, yeah, the size of the bounding sphere. This is valuable if you're doing culling for meshlets, whether it's frustum culling or occlusion culling. So the third thing that you're trying to balance, you might be trying to balance, is the normal direction. Or the spread of the normal directions, really. Because if the spread is really large, then at least one of the triangles will likely be visible, or will be non-backfaced culled, let's put it this way. And so this reduces the efficiency of the cone culling. So my current hypothesis is this. Let me talk about the problem. So there's three factors that you're trying to balance. And the problem is that the first and third one are in basically direct conflict. And sort of the third and second to an extent, but not this much. And let me explain what I mean. Like I did tests on this kind of stuff. So it's very so okay, if you have like a low poly mesh, maybe I should start with this. If you have a low poly mesh, in general, the hopes of getting the cone culling to work efficiently are pretty slim, because you will end up having a lot of triangles with just sufficiently different normal. Like, so if you have a cube, right? Like the only way cone culling can be efficient is if each face of the cube, the 4 vertices with 2 triangles, are in a separate meshlet. Because then for each meshlet, you know, the normal direction is like, the normal spread is very small. It's basically 0, so it's, okay, great. Obviously, this is a very inefficient meshlet distribution because each meshlet is really small. Right, you aren't just trying to maximize reuse. I guess I should have said 0. You're just trying to pack maximum number of triangles, right? Oops. Potentially vertices as well, but like meshlets with 4 vertices and 2 triangles are not good meshlets. So you can see that on the cube, right? If the entire cube is in a single meshlet, cone culling just doesn't work. And if individual faces are in separate meshlets, cone culling works, but the split is very inefficient. So your cone culling is probably penalizing actually the execution speed. Now, if you tessellate this cube a lot, then the problem goes away slowly, right? Like the more faces you add to this cube, the better it is. But so then if you look at the high poly meshes, so for low poly meshes in general, cone culling is, like it rarely works really well. And the reason why is, so if you look at high poly meshes, it's very, very common to have, like the reason why, hopefully, the reason why you have a lot of triangles isn't just because they're tessellating planes, right? It's because there is detail there. And so detail implies changes in curvature and things like that. So you could have often, like things like that, right? Like this is how your surface looks. Now, if you look at any small patch of this, or at most small patches of the surface, the cone spread is pretty bad. Like if you look at this patch, and let's say this is your meshlet. Well, the problem is here there is normals that are almost orthogonal to each other. And so there's very, very few camera directions, very, very few camera positions, I should say, but like whatever, where all of the triangles in the meshlet are just backface culled. The way to build a good meshlet distribution for the point 3 is to try to restrict the normal spread between the individual triangles in the meshlet, right? Which effectively means that you are doing something like this. You're saying, okay, there is this surface which it's pointing roughly in the same direction, so it belongs in the meshlet, fine. Let's find other surfaces with similar normal direction. Okay, there's like this stuff which is reasonably close, and then there is like maybe this stuff, and then maybe this stuff, right? And depending on the tessellation of your geometry, or like even worse, if the geometry is tessellated appropriately for the curvature, meaning the vertices that you have actually add sufficient detail, the odds are that trying to optimize for the normal direction mostly forces you to split very, very small patches from the rest of the geometry. So you end up with cases like, okay, here's like what is it, 1 2 3 4 5 6 7 8 triangle patch. Okay, I guess it lives in this meshlet, and then some other stuff lives in this meshlet. And so this penalizes your vertex reuse, which is bad for highly tessellated geometry because you spend more time transforming vertices and stuff like that. So my current hypothesis is that because the cone culling stuff is kind of like, it's really hard to get it right, and often it just can't really work well. My current hypothesis is that you should focus on the points 0 through 2, and then mostly just ignore 3, maybe complete. My plan is just to completely ignore 3, to be honest. And then if you have a dense mesh with a lot of triangles that are next to each other and close to coplanar, then it sort of will like cone culling will mostly work out, right? You could maybe use the normal direction as like a slight bias, like if you have two triangles to pick between and both of them don't increase the bounding sphere of the cluster by too much, but the cone is like sufficiently different between the two, then okay, it's an obvious choice. So maybe it's fine to introduce the normal direction into the computation, but just with a very, very small factor, right? Like it's almost, in my opinion, it basically becomes almost insignificant. But it's probably worth to like include it. It's just that everything else likely comes before it. And the other interesting thing is this. So assuming you're really serious about, rendering a lot of geometry really quickly and stuff like this, you kind of must have occlusion culling. And so if you do have occlusion culling, in a lot of cases, how do I put this? Like occlusion culling in many cases is a stronger culling technique, substantially stronger culling technique than normal cone culling. So the way you can look at normal cone culling is it's very, very cheap, so you might as well just do that. it can, if you do it first, it can, for example, reduce the amount of lookups that you do in the occlusion buffer, which saves you a bit of the calling time. And sometimes it helps you call a few things that you wouldn't have called otherwise. For example, if you have a sphere, then it's kind of unlikely that you are going to call the boundaries of the sphere with occlusion buffer, because there is like limits on the occlusion resolution and stuff like this. So maybe for things like that, cone calling gives you a bit of an extra calling on the edges. Not too much, but maybe it's enough to kind of justify the cost, right? So yeah, anyway, this is kind of how I think about this right now. I haven't finished doing this though, so maybe some of this stuff is just wrong. Is there general applicability for WASM in a normal website? Is it already used more often in the wild? How do you predict future in that regard? So to my knowledge, WASM isn't very widely used right now on the web. And the way I think about this is WASM is really, really cool because it expands what is practical on the web. People build all sorts of crazy stuff like, emulators and whatnot, and you could imagine running. So let me back up. The way web started was, here's a website, it has a bunch of information on it, here's a bunch of links. And then at some point, maybe people started adding animations to the UI, like small transitions and stuff like that. All that's fine. However, so the web page that I have open right now, which happens to be YouTube, is already not quite just a standard web page that you would have imagined back in the day. There's this like chat that is completely interactive, like real time. There's this video in the top left corner. So it's kind of already not quite a normal web page, right? But then you can look beyond this. You can look at Slack or something like this, Gmail, Google Docs. These are effectively full-blown like applications, right? And so I feel like when you go into the realm of applications, there's more use cases for WASM, because there are some people who are trying to build full applications in WASM, just like no web whatsoever. And that's kind of cool. I don't remember this off the top of my head, but somebody built a really, really cool online web editor in Rust. And it feels honestly pretty good to use that editor compared to anything else that I've used that ran in the web browser. It's like amazing. And so I feel like there's space for this kind of stuff. And I also feel like there's space for things like, okay, so maybe you're writing Google Docs, right? And maybe parts of this Google Docs application are actually a C++ or Rust or whatever library that is compiled to WASM. And the reason why you did this is because it runs faster. Maybe it's easier to maintain because maybe you're sharing this code with... so Google Docs might be not a great example because Google doesn't have a product like this. But so Microsoft Office, right? They have an online product now and they have an offline product. And it's actually very interesting to share large pieces of this code that do things like, okay, here's like a file, like PowerPoint file, let me parse that. Like you don't want to write this code twice, ever, right? So in this context, WASM is interesting. WASM is really interesting with anything that involves graphics for obvious reasons, right? It's just like performance is... in WASM, performance is high and it's predictable, which is really important. It can reduce load times on the web pages, right? You open a web page. If your web page right now comes with like 5 megabytes of JavaScript, it's not just that you download 5 megabytes of JavaScript, it also takes you a lot of time on low-end devices, especially to parse that. Parse that and compile that. Then there's this JIT that doesn't start with in fast mode and then uses some course that you have to compile it in background and stuff like this. Like WASM, I think, is a beautifully simple technology compared to the rest of the stuff that people built around the web. So in that sense, I am kind of really happy with that. But I don't really imagine, like New York Times or something using WASM. I mean, maybe they end up using WASM because they use some library, that library happens to use WASM, but I don't think it's big in that sense, right? I don't think it's big in the sense of, oh, it's obvious, like today it's obvious that a website is using JavaScript, right? There's just like, I mean, you have people who don't use JavaScript, but it's just unthinkable to not do that, really. It's obvious that a website uses CSS. So I don't think WASM really will be ever something like that. But yeah, it makes the big thing that I'm really happy about is code reuse. Honestly, you can write a library now, and you can cross-compile it to WASM, and you can write a thin JavaScript wrapper around this. And your library is now usable on the web, which just increases the kind of reach of the library, right? And there are other weird examples. So I'm writing this library mesh optimizer, right? And that has a command line tool, gltfpack, that can take a file and then produce a different file that's smaller. And it took me like 10 minutes to build that library into a JavaScript file that is now an NPM package. So what you can do, I don't know if this will work from this is it's like WSL, but NPM I think is an actual executable or whatever. I'm not sure NPM actually seriously works here because I didn't install native NPM. But you can do like NPM install gltfpack, and then you can just do gltfpack. I have it installed, I think. So let me just check. So So I can just run this executable, right? But I think. Oh no, okay. I lied. This is not a okay. All right. So I can write I can run an executable from my command prompt. Is there a way to do where in Windows? How does this work? Is there a where? Okay, there's where. So if you look at what gltfpack is, it's actually a batch file. We can even try to open it. I don't actually know what it contains. Okay, so there's a batch file which is just a wrapper that says run node.exe, so node.js, right, with the JavaScript file. And if you look at this JavaScript file, I didn't write this file. I just built that file from my source that was never designed to run in the web environment, but it still runs and it has access to files on your local file system. And so it's an interesting way to distribute executables. And the other fun thing is that this gltfpack executable is running inside node process, which means it's basically a sandbox. Like it has access to the file system, but it can do, which technically I guess means it can do a lot of evil things. Like if I didn't give it access to my whole file system, then it would be really strongly sandboxed. Like it would be hard to imagine it doing a lot of harm to your system. And it runs the same on all operating systems, right? Node is different, but this thing is the same. So it's kind of interesting. There's this whole weird world of using web technologies as a way to distribute libraries and applications, potentially beyond the web itself. It's, you know, it's interesting. So yeah, I don't think it has a lot of future in the broad web, like every single website obviously uses WASM, but there's a lot of nice things that WASM enables, and I think it makes the web stronger for it. Talks lined up with ARM on Reboot. I don't have talks in next Reboot. I don't even know if next Reboot is happening. I didn't look. Reboot was a fantastic conference because the location was fantastic, but the tech track was weak. And it just felt like this conference is not really for programmers. It's not really for engineers. It's for people to hang out, but like the issue with that is it's kind of fun to hang out with people from different segments in your profession, but you have to kind of expect this going in. Like you shouldn't expect to go to Reboot, at least the way I think two last Reboots were, and you know, get a lot of deep insights about technology in any shape or form. So yeah, anyway, I had an ARM talk that was scheduled for GDC this year. Obviously GDC is cancelled. There's gonna be a video recording of this talk. This talk is not gonna be super new though. It's sort of a lot of the stuff, most of the stuff that is going to be there, I think it's either in my reboot talk or in my blog post slash article slash whatever you want to call that, which is on my blog, which is a chapter that I wrote for a book a couple of years ago, but it's now freely available. There is going to be a talk, or there was going to be a talk with PowerVR though that I was going to do on GDC. So the GDC is cancelled, but the talk isn't. So there is going to be a joint talk with PowerVR where I talk about some of the lighting work that we have been doing. So that's going to be fun. Update, expand the post-processing effects library, post features, bright phase 3. Yeah, maybe. I mean, we are shipping depth of field at some point in the next couple of, I don't know. We were supposed to ship it like now, but things happened, so I don't know exactly when it's going to ship, but there's going to be depth of field. There's going to be some other post-processing effects that we have planned. Nothing super revolutionary, but there's going to be some stuff that's done. Noticed you're a heavy C++ user. What do you think about Rust language? So, I have mixed feelings about Rust. The first thing you should know about me and Rust is that I actually used Rust before it... Okay, I used Rust after it was cool, but before it became actually official. I used this in pre-1.0 days. I used it around 0.4 or something like this. I don't think I was following it for a while. I'm still following the developments in the language. I was following Rust, I think, since it had an OCaml. Like, I mean, it had an OCaml compiler in the very beginning, but at some point, while it still had an OCaml compiler, so it was not self-hosting yet, I started following it. And then I not started using it, but I used it a bit to write some graphic stuff, just to kind of experiment with this. And I wrote... basically I wrote like a graphics application with like Martian cubes and whatnot, like OpenGL render, that kind of stuff. And I think I wrote, like I had to look at some libraries, and this was before Cargo, before Rust 1.0, like effectively before Rust, right? At that point, there were things that I liked about Rust, and there were things that I disliked about Rust. It was an interesting new language. This whole borrow checking thing is really, really... I hesitate to use the word revolutionary because, of course, it's been done before, and of course, it's not a completely new idea, but it's the first production implementation of this idea. So I am going to use the word revolutionary, sure, why not? It's in general a modern language. Now, when I used it, it was like before Cargo and stuff, so it was a bit less modern than it is today. But even when I used it, it was things like, okay, you want to write a unit test. The way you do it in Rust is, so I haven't written anything in Rust in the last 2 to 3 years, so beware. But you do something like test function my cool test, and then you say, something, and then I guess you say assert something and whatever. And now the way this works is I think you run cargo test x, and then this just compiles and runs a unit test. And then if you don't build this in the test mode, tests don't run. And they aren't even compiled. It's really simple. There's no reason why C++ couldn't have done this like 10 years ago, 20 years ago. Go does something kind of the same, I think. I don't think before Go I mean, there were like C# and Java sort of libraries that did stuff like that, I think, with attributes. Maybe Python does something like this with attributes. But like in native development land, basically before Go, this was just unprecedented. It's like, oh, you want to write a unit test? Well, duh. Here's 10 different unit test frameworks that are available. Pick one, and then write this whole separate setup. And there's a lot of ceremony around this. Whereas in Rust, it's like things like that, right? And there's a lot of things like this that Rust makes really simple that have nothing to do with Rust, as in there is special magic sauce about Rust that nobody has ever done before at scale in production, right? Which is specifically the borrow checking. Maybe there are other big things like that, but I'm not actually sure that they are. I don't remember off the top of my head. I'm not like I haven't used Rust. I haven't written anything in Rust in the last 3 years. I've debugged the Rust program a few weeks ago because I had to. And I read Rust blog posts and stuff, but I don't actually actively write in the language. So if people who watch this are like, oh my god, what are you talking about? There's this really revolutionary thing that Rust did that has nothing to do with borrow checking. Like, maybe it exists. I just don't know off the top of my head. But yeah, like fundamentally, I think what Rust is it's a really nice modern native language. So no runtime or really thin runtime rather, compiles to native code, supports multiple architecture, stuff like that, like no garbage collector. Lots of good, boring, I shouldn't use the word boring. People are sensitive about this stuff. Established ideas. So, I mean, there's a lot of stuff really. So let's look at this. So for example, when it comes to generics, Rust doesn't do anything new in that regard. Maybe some people think it does, but really it doesn't. But it takes two good ideas from two different worlds and blends them together. And even that blend has been done before. There's nothing new about this. It's a good idea. Like the first thing that Rust does, just taking generics as an example, right? So the first thing that Rust does about generics is that, I forget what the official term for this is, but effectively the implementation is type checked without instantiation. So my handwriting is really horrible today. What this means is that you don't have to wait for a generic function or construct to be used before saying, oh, it's actually valid. C# does this. A camel does this. C++ does not do this. Java has somewhat weird generics, so like who knows whether it applies there. C++ is starting to do this with concepts. However, my understanding, I'm not an expert in C++ at this point, but my understanding is these concepts actually don't really guarantee that. Like they were supposed to guarantee this, but they couldn't ship that feature, so now there's concept slide which don't. So this means you write a generic function, like it will work, there's good compile messages, you spend less time doing type checking because you can type check the thing once. And then the other thing, which is good, some people in the Rust community think it's bad, but like for the domain, I think it's good. And they're experimenting with other options, is that instantiations basically the instantiations are specialized. So it's specialization of instantiations. Oh my god, whatever. What this means is that, so OCaml doesn't do this. C# does not do this when it generates IL. It's kind of does this when it generates the native code, but it's a bit constrained, so it doesn't really fully do that. But what this means is that if you have a generic function and you use that generic function with a specific argument type, the performance of the resulting code is the same as if you just wrote it without the use of generics. And so C++ does do the second thing, but does not do the first thing. Like a camel or whatever does do the first thing, does not do the second thing. The blend of these ideas means that you can write generic code, you trust your generic code to work, and you trust your generic code to work fast, which is nice. But then people in Rust take this license to write generic code and write these completely abominable constructs that, you know, you never would have written in C because there's no generics. You wouldn't have written them in C# or a camel because there's not enough expressive power. Or maybe in a camel there is. In C# there isn't. Not enough expressive power in the type system. People do write this in C++, but a lot of people scoff on that because it's just like crazy, but it's much harder to maintain. And so in Rust, it's more acceptable, I feel, to write crazy generic constructs than it is in C++. And I'm not very happy about that. But like anyway, so there's a lot of good established ideas that Rust takes and executes really well. So that's great. And there's this one, as far as I know, I'm gonna say novel, but you know, caveat emptor. I don't think Rust invented this fully, but for sure, whenever you have an invention, it's one thing to come up with an idea and to write a research paper and to write even a research language on this, and it's another thing to ship an implementation of this idea in a production language that millions of people, I doubt it's millions of people, but a lot of people, less than millions, use, right? So I think from that perspective, it is novel. Like just coming up with an idea is not sufficient. Just writing a proof of concept implementation is not sufficient. So one novel idea, which is basically the borrow checker, quote unquote, which leads to two things really. It leads to memory safety, which makes code more secure, and it leads to fearless concurrency, which is a bit of a strange term, but it really means that data races in Rust are way more explicit than they are in C++. And so you can, generally speaking, trust people to just write code, and then the code probably doesn't do horrible, unspeakable things to your heap or whatever. And good execution, right? Oops. So all of these things are good, right? So like, why am I not using Rust right now? So there's a couple of reasons why I'm not using Rust right now. So the problems that I see with Rust, they are roughly as follows. So the biggest problem I see for myself is friction. And friction comes in many ways. I think there is probably three. Hold on. I was thinking of 3 ways, but let me write them out. Three ways that friction manifests for me in Rust. Oh yes, 3 things. So one, there's like the 2 more important one and the 1 less important one. So one is just friction writing code. And not just writing code, writing low-level, performant code. And when I say performant, I don't mean like code is fast. I mean like the code tries to take tries to be reasonably close to optimal on the target hardware given finite engineering resources. Now, why is that? There's a lot of, there's a lot of small things in Rust that, so there's this whole borrow checker, right? But actually borrow checker is hard on people in large systems, like it affects large scale design. I don't actually know that it it affects kind of micro stuff, but I don't know, what's the two examples here's two examples in one sort of. And again, like, people who know Rust, they will probably look at this and be like, you don't know what you're talking about. But this was my experience writing Rust code like back in the days, right? So like 3 years ago, whenever that was. And Rust hasn't changed much in these areas, and I know because I follow the language. So there's this simple thing which you can do, which you can say, let me take an array and let me index with an index. Oh god, okay. Like, straightforward, every language does this. Rust has two things. In high performance code, you see this stuff a lot, because high performance code is built around arrays for memory locality reasons and whatnot. So in Rust, there's two things that get in the way of this code. One is, from the point of being able to run this code, turns out in Rust there is no conversions between integer types, which I've always thought it's a great idea. Like, when I was writing my language prototypes that like never released or whatever, I was like, C integer conversions are just horrible. Like, surely you don't need to use them. But in Rust, the index has to be what's called the usize, which is a 64 or 32-bit integer depending on your bitness. And so, for example, if your index is, say 8-bit, or 16-bit or 32-bit integer, well, you can't write this code. What you have to say is, like, index as usize. And this just drove me slightly nuts. Maybe it didn't help that I was writing like a Martian cubes implementation or something, but it's just, when every line of code you write array of index and the compiler is like, oh, no, you can't do this, you have to cast usize, and you're like, oh my god, why? Right? And I understand why, to be clear. Like, I know very, very precisely why this is good and why this is bad. It's just it really hurts ergonomics. And the other problem with the array of index, of course, is that it's bounds checked. Like, there is an implicit in release mode, there is an implicit comparison with an array size there. And there's like three coping strategies for this in Rust. One is maybe LLVM will figure it out. I've been writing performant code for more than 10 years now. Let me tell you, I have, generally speaking, limited trust in the compiler. I know fully well what optimizations compiler does well and what optimizations it does poorly. And in trivial cases, LLVM will figure it out. However, in many cases, it won't. And what this means is, like, it's hard to catch the stuff in the profile, because it's not like there is a function that takes a lot of time. It's just your code gets uniformly slower. I think people did research on this kind of stuff, and the slowdown is like, there's a specific margin for this, it's like 5% or whatever, but it depends on the type of code that you write. A lot of code that I write, the penalty might be more substantial. So the second coping strategy is use unsafe. And there's two problems with this. One is, really the problem is basically that if you use a lot of unsafe in your code, then this whole concept of safety starts becoming slightly less useful, because the idea of unsafe is that you can have very small contained kind of places where it's used, and then you can audit them to make sure your code is correct. But if you have these large swaths of code that's just unsafe, then like this benefit of Rust kind of is less beneficial, which is not great. And then the third one, which people use, like filter, basically iterators. So filter, like, I don't know, zip, for each, I don't know. I don't know what the full set is. I dislike this style of programming for performant code. There's a lot of abstraction here that you trust the compiler to be able to elide. It emphatically doesn't elide this if you don't have optimizations enabled, which is not great. And I don't know, I was in love with this when I was writing F# code like 5 years ago, but I kind of grew less fond of it because it kind of became this, mental. It's like this puzzle. Oh, I'm writing this code, but no, I'm not going to use a for loop here. For loops are for chumps. Instead, I am going to figure out how to express it in like loop combination. How is this thing called? Streams, ranges, loop. In C# it's called link, like, I don't know, whatever. However it's called, like, as a composition of the stream filtering and combination operators, right? And it's just that it's really, really cute when you start doing this. It feels like this awesome power that you have gained. And then over time it feels less like a power and more like just you're doing this work for no particular reason. And performance implications are really unclear. Anyway, sorry, I spent way too much time talking about this, but like there is cases where basically, like, okay, in C++ it's also not that great, right? Writing CMD code in C++ is a disaster, and Rust hasn't fixed it yet, but my understanding is they're gonna fix it, or maybe they have made it much better already. Like, I forgot, I stopped watching the Rust CMD effort I think half a year ago, and I feel like half a year ago they haven't added the library to the standards one yet, but maybe at this point they have. So like, I trust Rust to figure some of these things out. It's just that it was kind of a frustrating experience for me. So the second point of friction for me, which is big, is friction of other people when using my code. So there's this nice cozy community around Rust. I don't really write applications. Mostly I write in my spare time, right? I write libraries that other people use. So there's this cozy community around Rust where you publish your crate to crate.io and then you add it to cargo config and then you're done. And in that ecosystem, like, libraries really thrive. But when you say, oh, I'm actually not gonna write C++ code anymore, I'm gonna write Rust code. Okay, how do other people use your Rust code if they aren't using Rust? And then you have two modes of operation. One is, I'm a Rust evangelist, I don't care, the world without Rust either doesn't exist, or I begrudgingly acknowledge its existence, and will do my darndest to kind of make that world disappear over time, and I'm not of this mindset. And the other mode of operations you can be in is I want to help people. And when you want to help people, this means, for example, you figure out how to use your Rust library from C or C++. But if you have a complex interface to your library, then it's hard to write a good wrapper around this. And so the problem exists in the opposite direction. Like, you could say the same thing around C and Rust, C++ and Rust. Like, oh, you wrote a great C++ library, but what about people writing Rust code? But I just feel like right now, in terms of the volume of use, in terms of the benefit to humanity, for the lack of the better word, like, if you're trying to maximize the number of people who your code will be useful to, Rust is just not the best language for this purely from this standpoint. And like, you can solve these problems, you can write wrapping headers, you can use CABI to compile the code, etc. It's just it adds more friction to writing the code, right? And I don't like that. And so there's the third type of friction, which is tooling. And part of this is just, hey, can I just open a Rust program in an IDE and have it just run? I use Visual Studio a fair amount of time, although I'm starting to use it less and less. And so maybe if I used Visual Studio less, I wouldn't be thinking about this much, but you know, like to my knowledge, there's not just slam dunk, oh, I'm just opening Rust code in this IDE, I have good completion, I have everything. Maybe it exists in VS Code. I can't personally use VS Code, it's too slow for me. Like, I can't enjoy writing code when I write it in VS Code. So that's a bit of a problem. And also, with tooling, there's a specific thing that I'm really sensitive to, which is compile time. And Rust is a slow language to compile. And you would be like, what are you talking about? You write code in C++. C++ takes forever to compile. Now, if you're really careful about the C++ code you write, it compiles fast, like way faster than Rust, to my knowledge. Maybe I'm wrong. But my impression, so this is the thing where I'm like hesitant to just go and explore this, because compile time was a big problem for me in Rust before. And they made the compiler faster, and they're still making the compiler faster, but it's just, I'm just worried that all of these improvements are really small and incremental. And you know, yeah, like we made the compiler 10% faster, cool story. I want the compilers like 10x faster. Well, 10% is just not good enough. And like, you can tell me all of the things about how Rust does way more work and stuff like this, but it's just not really true. Like, it's true, but it's also not really true at the same time. Now, there is significant, like, Rust community understand, parts of Rust community understand that this is a big problem, either a big real problem or a big perception problem. There's large initiatives that try to make this better. Like, there is a new code gen, for example, that for some types of Rust code makes them substantially faster to compile without optimizations, which is a big thing because it means that you can iterate on the code faster. So anyway, I've spent way too much time on this, but the short of it is, there's this curve. There's these two curves for me, okay? Three curves for me. So there is one curve, which is how comfortable am I with the C++ code that I write or I see other people write in the environment that I control, like, you know, at work and whatever. And this curve, generally speaking, over the past, you know, 15 years or whatever, it probably went like this. Then there's the curve, which means I actually have reasonably high confidence in the code that I write today. It's comfortable for me to write the code that I write today. I'm used to this. There's this curve, which is what's my perception of how easy it is to write Rust code. And you know, I haven't heard of Rust for years and years, but like at the point where I got introduced to Rust, which is, say, this code, my perception of how easy it is going to be based on some of my experience writing Rust code, right? Like, I didn't just read blog posts. Again, I wrote like 10,000 lines of code or whatever of Rust. My perception is there's this cliff, right? And then it kind of gets better, and then this is my current perception. And maybe it's getting better, but I haven't used Rust in 3 years, so I don't know. Well, I know some ways in that it did get better, but really I have to try again, right? But there is this third variable, which is how comfortable am I with C++ as a language, not in code that I write, but in how the language matures and is being developed and stuff like that. And so C++ has been stagnant up until 2011. So for the first like 5 years of this or more, you know, there was like some level of comfort, which was like, I don't know, whatever. I'm changing the Y scale, and also all of this is like not scientific. But let's say it goes like this. As in, I look at a lot of the C++ developments, and a lot of them I just quickly lose faith in C++ maintaining the values that I hold. I think C++ will survive. I don't know that I'm going to be comfortable writing in C++ for much longer. Which is to say that right now, it's hard for me to justify just going all in on Rust. I'm happy where I am. I'm happy writing really high performant code that has reasonably few bugs. You know, it has its fair share of bugs, but it has reasonably few bugs. It's fast. It's reasonably fast to compile, you know. I'm not happy with where C++ is going, but I am also not seeing Rust right now as a revolution along all of the axes that I care about. So because of this, I'm not fully ready, right? I feel like maybe in 5 years, I'm gonna be like, C++ is so bad now. And Rust people have made so many good changes that it's just more of a no-brainer. But I'm not sure, for example, what to do with this bit. Like, I think this bit says the world has to catch up for me to feel happy writing Rust code and seeing people use my Rust code in production, right? So maybe it's already there. I don't really have that perception yet, so we'll see. That was a long answer. All right. Right way to support multiple graphics API in game. Write high level render for API. Use low level artificial API with translation layer to real APIs. Yeah, I mean, like, so okay. I feel like the real answer has to be a translation layer, but now there's the questions of how large the translation layer is. Today, the landscape of graphics APIs looks I want to take a 1 minute break or 2 minute break or whatever. I want to brew some tea and stop talking for a couple of minutes because it's it's a convenient time because it's a break in the topic. So let's do that. All right, I am back. I realized I forgot to say one thing about Rust. So I think it doesn't help my current perception of Rust that there's two things that are going on. The first thing is for the last, a bit less than a year, I was writing this whole like compiler technology stuff, right? There's two parts of this. One is the high level part, which I think Rust would be a fantastic language for, probably, which deals with a lot of like abstract syntax trees and pattern matching and IRs and God knows what else. There's another part though, which is this really crazily fast interpreter. To my understanding, it is impossible to write this code in safe Rust. It must be possible to write it in unsafe Rust because like it's the same LLVM code gen and stuff. The reason why I say that is twofold. One is I just see the amount of crazy stuff that I have to do where there's completely impossible for the compiler to actually like validate that the pointers are correctly accessed and stuff like this, but there's sufficient testing around this that I feel comfortable with that code. Well, I'm like wary of this code, but it doesn't prevent me from working on this code. And I just see all of these things where I have to optimize this in this way, and I mentally map this to what I would have to do in Rust, and in Rust it would be, oh, I guess I either can't do this or I need to use unsafe code. And also, the fastest interpreter in Rust that I have seen of a dynamically typed, well, of Lua specifically, is like substantially slower than the Lua interpreter, not our interpreter, like Lua basic interpreter. Which just doesn't give me confidence. So I'm working with this really crazy fast code, and it's just based on what I've seen. I'd have to use a lot of unsafe. And the other thing that's happening is I see these spikes in Rust community where somebody publishes a library with unsafe. There was this recent drama like a few months ago where a developer of a library basically had to stop developing the library because they used a fair amount of unsafe code, and it would come up on Reddit once in a while, and somebody made the GitHub issue and they closed it. There was this whole like bad communication happening where the developer of the library was getting frustrated. Other people felt that it's really important that this library conforms to the standards that they have, and as a result, the developer just said, well, I just can't take this anymore. Like, it's just making me actively, like, you guys as a community are making me actively upset. Now, to my knowledge, kind of the grown-ups in the community kind of agree that there's just bad blood on both sides and bad behavior on both sides, and it's really kind of terrible that this whole situation happened. But it kind of just makes me wary, where I feel like if I write code in C specific, so C++ is also terrible for some of the similar reasons. But I feel like I don't have to apologize to anyone apart from Rust people and C++ people, C++ zealots, I guess, for writing just really fast code in C. And in Rust, I just have this fear, and I'm sure it's unfounded, but I've just seen it happen multiple times where some segments of the community are just not, there's a bit too much kind of like the good passion turns into a bad passion, and it just feels sad. But like C++ has the exact same problem. So this is the point where I feel like when the red curve that I drew there goes low enough, I'm gonna be like, you know what, I'm just done. And like if I'm done, the only ways that I see today are C or Rust. There's other languages like Zig, which I'm not a big fan of, and there's nothing else really. So I feel like it's either stop writing C++ and start writing C, which is slightly weird, but maybe at this point there's C23 that, I don't know, is slightly nicer. Although I kind of like C, or it's stop writing C++, start writing Rust. Like, I feel like it's kind of inevitable that at some point I'll probably start writing Rust. It's just that this time has not happened. Anyway, right, the rendering APIs. So the landscape, I feel, of the graphics APIs today looks sufficiently complicated that there is no option for you to just write your high-level rendering code using multiple APIs. Even if you're an expert in all of these APIs, even if all of these APIs were really ergonomic and convenient to use, there's just too many of them, right? So assume you're working, okay. First possibility, you're working on a console class game. Usually there's two worlds that are somewhat disjoint, there's console and then mobile, but assume you're working on a console class game. Okay, you probably want to ship your game on PC. You could decide not to, but there's so much similarity between PCs and consoles at this point that even if it doesn't give you the extra, like, you know, half of the revenue or whatever, which it won't, but even the extra 20% or whatever, like, especially given the fact that the effort is just from, like, if you have a team of 300 artists making art, it's not, it just feels like you have to do this. I don't know. So assume because of this, and I think this is true of all of the major releases, assume that you're shipping on PC, Xbox, and PlayStation, right? Because of this, you already have to write code in DX12 and PS4 API and PS5 API, which I don't actually know if these are the same or different, at the minimum. And you might want to strongly consider also writing the code in DX11, just because DX12, depending on your audience, DX12 might substantially cut your kind of market share. Now there's this possibility to use DX12 on Windows 7 now, so if you can take this, you should take this, but assume you can't. And also even assume, so okay, like just assume this basic form, right? Okay. Still, it means that you're writing your high-level rendering code twice, and high-level rendering code is really complex these days. Like, there is like just a lot of stuff there. And the high-level code that depends on the graphics API also gets really complex. But this is the basic case. Like, the actual realistic case, I think, looks like this. So you need DX11. And also, either you have contracted some company to port your game to Mac, or you haven't. Assume you haven't. So then you have a Metal backend. Also, this whole Google Stadia thing is taking off, and people from Google come to you and are like, oh yeah, you should really launch our game on Stadia. Okay. And there's like things you can do. So you can port your game to Vulkan and then go Vulkan Metal using the Molten VK, which I don't think it's a good idea, but you can do that. Also, if you're on Switch, you also have to do either Vulkan or GL or Switch API. So we'll just assume Vulkan, although I don't know how well Vulkan works on Switch. So, like, it becomes unsustainable almost immediately. And if you're on mobile, you also have to, by the way, use GL or GLES rather, because on iOS you actually don't. There's just almost no devices at this point, for us at least, that use OpenGLES. So if you're shipping a new game on iOS, just do Metal only. But on Android, Vulkan for us is like half the audience, so you just can't afford to do Vulkan only either. And if you look at something like Fortnite, I mean, that's basically what they do. And so there's just no option to not do this. as far as I'm concerned. Now there's caveats. For example, you can be really religious about, oh, the only way high-level rendering code can work is through the low-level rendering abstraction, and the low-level rendering abstraction is exactly the same between all of these platforms. Or you could say, well, the low-level rendering abstraction is mostly the same, but there are classes of APIs that are not available on some platforms or whatever. Or you could say, well, the low-level API is roughly the same, but you can actually get a native handle to like DX12 context or whatever, and so some parts of our code are actually written using just raw API. I prefer the middle ground approach where you try to not write like native code, code using these APIs natively, but you try to make your abstraction layer flexible, and in some cases it means there are parts of the abstraction that are just not available on some of the APIs and you have to duplicate your rendering code. So this is the approach that I prefer personally. But yeah, I just feel like there is no real option to rewrite high-level render. Unless, I feel like the only option goes like this. You wrote your game using DX11. You shipped it. Great. Then, the game sold a lot, and you're doing a console port. Maybe you're doing the console port only to PS4 because Sony paid you a bunch of money to do this. Probably you're just rewriting, like you aren't going to do a rendering abstraction, right? So if your code is short-lived, or if you're just delegating, like if you just paid a lot of ports for Mac, for example, are not done by the studios themselves, they're done by third parties. So if you're just paying the third party to do this, like you don't really care what they do, right? But if you are working on technology that spans multiple games, I feel like you kind of have to do this. And there's an art to kind of designing a good rendering abstraction, but you can do a reasonable one. What do I think about Unity and their attempt to go ECS all the way? So, okay, caveat emptor. I'm super not an expert in Unity. I looked at their dot stuff, but I looked at it casually. Like I watched a couple of GDC talks and I looked at a couple of pages of documentation. I think it's really interesting what they do. The biggest thing I heard is that it's hard for people to actually use these frameworks with this style, right? I mean, this sort of makes sense. Like it fundamentally changes your mental model. But I also find some of the So mini rant. If Mike Acton ever watches this, which I don't think he will, I'm sure he'll post on Twitter how I just don't understand this. But I kind of was surprised in a not a good way when I looked at Unity's transform graph implementation using dots. I just felt like in so many steps of the way, the right choice was to say, no, we shouldn't do that. And not knowing Mike Acton too well, but having spoken to him a couple of times about things like that, and having watched a few of his talks, I was just genuinely surprised as to how complicated, and complex is a loaded word, right? And I'm sure if we had a discussion about this with Mike, which we have not had, we would find a common ground, as reasonable people usually can. But I just was surprised at kind of the complexity and a bit of the, I guess, monstrosity, honestly, that so Mike Acton has had this really famous talk about C++, where he criticized the Augur implementation of the scene graph. I think all of the critique was valid. I think you can do a very equivalent post or talk or whatever, just destroying Mike's scene graph thing in the same way that he destroyed Augur's. And so I was unpleasantly surprised with that. But the framework itself, I mean, from what I've seen, it's kind of interesting. I I'm really curious as to I find that approaches like this work really well when you are trying to be really disciplined about the system that you're making. So, like transform graph or something like this, small scope, can figure out what the right features are, doesn't have scope creep, stuff like that. Cool. My feeling is that this tends to break down when you're writing quote unquote gameplay code where, requirements change all the time and it's not clear how to decouple things in a nice way and stuff like that. So, what I'm really curious about is what's the kind of what the experiences of people using this stack beyond just cute demos. I think all of the stuff that I have seen so far was demonstrating the power of the stack. You can do a like 100,000 Boyd simulation doing um, steering and avoidance and all of this stuff. Awesome. You can do a physics engine that processes a lot of bodies in parallel, etc. Awesome. I'm kind of curious to hear more about. We had this complicated game with lots of behaviors and stuff. Here's how we decoupled it. Here are the things that went easier than they were in our pre-dots like behavior world or whatever. Here are the things that were really hard, and here's what we did about this. So I would be super curious to hear about this. From my standpoint, it sounds great. I'm like an engine developer, so I write a lot of code where the mental model is here's this constraint problem, here's limited scope creep, like figure out a good design, have to be as performant as possible, etc. Cool, sounds good. I'm really curious as to what the like Unity had been. The reason why Unity became big is because it was accessible. There's this whole tagline of like democratized game development that they've had, right? So it kind of feels like this is fighting that, but I don't know to what extent, right? And so I would be curious to know kind of. And like you can you can reframe your mind kind of around this paradigm. I just haven't seen so far super convincing examples of this general kind of thing applied to gameplay code. And so I'm curious as to how well this works. But people who run this, they have experience building games, so hopefully they can figure it out. Now, some of these games don't have the gameplay that's terribly intricate, so maybe it's not going to be that good. I don't know. But technically the work that they're doing is really interesting. Like I like the burst kind of stuff. Well, okay. So the thing I kind of dislike about this initiative is, and I said the same thing about Rust, I think, or maybe I haven't, but I wanted to. I feel like it's slightly more pretentious than. It's really, really cool and really, really technically impressive. But the one thing that stood out to me is that when they started, they were like, oh, yeah, this is like, we are going to beat ISPC, and this is like amazing vectorization technology and stuff like that. And like, to my knowledge, they use LLVM's auto vectorizer right now. Which, okay, maybe they do special magic around this, but I just did a stream like this week where I vectorized 3 functions or whatever it was in like a couple of hours that LLVM just gave up on. And so this just feels like some of the marketing around this feels slightly dishonest to me. But I mean, they are targeting people, I think, who mostly aren't able to like use alternate systems to the maximum extent, right? Like, I don't think they are targeting people who know what ISPC even is. So from that standpoint, it makes sense. It's just like there's this unease that I have about, well, I feel like you guys slightly oversold the burst thing. It's good from what I know. It's just that I felt like it's been sold as a revolutionary technology, whereas to my knowledge right now, it's not quite that. But that's fine. That's a really minor gripe. Like, I only bring it up because I started thinking about this and started thinking about, okay, so, let's hide the person who is spamming the chat with questions that are not part of the stream's discussion. All right. Jai. Jai. Embark. Okay. Yeah. A lot of people. So Embark is this. There's two game development studios that I know of right now that are trying to go really seriously in the Rust direction. So one of them is Embark. I think they still write some C++ code just for the like they use Unreal Engine, so have to. But yeah, and they're doing a fantastic job. My understanding is they're donating to some open source developers in the Rust game dev community, so they're sponsoring some of the work. They're making fantastic libraries. One of the people who works at Embark, Graham Whitledell, he made a library that wraps my C++ library in Rust to make it more accessible to the Rust community, which I think is great, right? So I think Embark people are doing great work, and I think Embark, there's very few jobs in Rust right now in game development, and very few jobs in Rust in general. So people who are excited about Rust, it's like these places feel like they're magnets. Like it feels like it's hard to hire Rust programmers because there's so few of them, but at the same time, there's so few companies that write in Rust that it's just so much more attractive of an employment proposition, right? It's like, oh yeah, do you want to move to Stockholm? No. Oh, by the way, you're going to be writing Rust code. Oh, Stockholm is a great city. It's just that cross-country locations are complicated. So yeah, great. They're doing great work. There's also Rad, which is not Rad Game Tools, but which is Radio Dawn. I mean, I don't know what they do. Like, they said that they're using Rust a lot and stuff like this, but I don't know, for example, maybe they're just not as, like, I don't know what libraries, for example, they have published in Rust or things like that, right? So, JI. I want to say that if Rust took the same stance on the on things like compile time performance that JI does, I would be like, all right, I'm just gonna start using Rust right now, and I'm just gonna trust you guys to get there. So really, really good things about JI, and in general, there is a lot of things in JI that I feel good about, in that, like they resonate with me. However, I don't think JI will succeed. There's a couple of reasons why. Well, maybe it will. I will be happy if it does, just to be clear. I just doubt this. And the biggest reason I think why I doubt this is that I feel consistently that Jonathan Blow, and maybe I'm wrong, I haven't talked to him about this. Again, maybe if we had a conversation, we are like reasonable people, at least, I feel like I'm reasonably reasonable. I think he is, so I feel like we would come to consensus. But I just feel like he consistently underestimates the value of the ecosystem and the complexity of building a rich ecosystem. And I just feel like it's the thing that a language can't succeed without. And so what I'm worried about is that the way this will work is that Jai will become public at some point in time. There's going to be a small community around Jai, and that's kind of where it will stop. Which, I think if you asked John, he would be like, I feel like it's a great outcome. If you ask me, I would be like, okay, should I write library in Jai? Some of the access don't have as much friction that I mentioned in Rust, around Rust. Some of the access probably have more friction. Is there going to be a really solid Okay, so when I started using Rust, there was no cargo. I witnessed the process of building cargo. It took years. It's a hard problem. because of that, it took years. Is Jai gonna have a good package manager? I just don't see why it would, right? Because I don't see John like valuing that much. I don't see him quite caring as much and thinking as much about this. And I also don't see him having the resources to do this, right? To do this really well. And so maybe JAI will get a good package manager, but it will take like 3 years from now. And yeah, so I generally speaking like Jai. Some of the syntax is slightly weird, but I actually like most of the syntax, or large parts of the syntax. It's very uniform, it feels nice. There's a couple of parts in the syntax where I'm just like, why? I think the biggest thing, the obvious basic thing for me, and it's all temporary, he keeps saying that. I worry that actually it's all permanent, but we'll see. Syntax decisions that are temporary tend to become permanent. But the biggest thing for the most striking thing for me, I just remember this vividly, was that when John was adding, I watched all of his streams. I think he's doing fantastic work. I just don't know how long the legs are of that work, right? When he introduced the character literal support, I just remember this in my head. We will not find that YouTube video, but I just remember it was like, okay, I need a character literal type. I don't have syntax for this. I guess the syntax should be whatever that thing is called, like single quote, apostrophe, whatever. Apostrophe character. So C puts a closing apostrophe. But really it's kind of stupid because you don't really need one, because there is only a single character, so why do you need to terminate it? And then he left it like this. And I think it's still like this. And in the stream, I think he used Emacs with C++ syntax highlighting, and it highlighted like the way it's highlighting for me right now in Sublime, with like the rest of the text just going. And I'm just looking at this and I'm like, dude, I know it's temporary syntax and stuff, but why? And the other thing, by the way, right, I remember the other thing. I was watching, he had a stream where he talked to Casey about parser technology. And I basically agree with everything that John said there. I have the exact same opinion on the parsers and stuff like this. But he was talking, I think in that stream, if I remember right, about the pointer syntax that he has chosen for his language. And he talked about how C syntax is slightly weird, and I agree. And he talked about his current syntax. But then it's just like, okay, so his syntax for dereferencing a pointer is less data. And the reason why is it because it gets a value out of data. And I'm like, okay, so C++ made a similar decision in iostreams. It's a terrible decision. It looks weird. Nobody will ever understand this intuitively up until you like beat that into them. No other language does this. Like, why are you doing this? And it's inconsistent. There is no other part of your language that has this less than keyword token that extracts data out of stuff. So why are you even doing this? And then he was talking about how, I think his problem was basically, let me try to reproduce this. I think his I think his syntax for grabbing an address is star something, and his syntax for pointers is star in. And he talks about how the fact that these are the same is good, and I agree with that. It's good to have uniformity. In C, it's weird, it's backwards. Like star dereferences a pointer, but puts a pointer around the type. But okay, there is a language, and I don't think it's just one language, but there is at least one language, which is called Rust, that said, this is stupid. What C did is stupid. What we're gonna do is do this. Actually, Rust also I think has pointers which work different. Maybe I shouldn't say that Rust was amazing here, because I think Rust has a star syntax also somewhere. But I think Rust did this. Right, so if you want to grab like a reference, or I forget what these things are called in Rust, to a type, you do it with an ampersand. If you want to do, if you want to grab a reference to an object, you do ampersand. And then you do reference with a star. I think this is how Rust works. And I was thinking about this, and I'm like, John, why don't you do this? Because this satisfies your criteria, where taking an address of a type and taking an address of a variable should have the same syntax. It keeps the star as a dereference operator. That's convenient. People internalize that. They know how it works. And it doesn't result in this abomination where it's less as data and I'm like, this is a left shift operator. I mean, this is a multiplication, but it's, whatever. Anyway, it's not a big deal, and as he says, it's temporary. I was just surprised. I don't know if he'll fix all of this. I'm assuming he will. And to an extent, all of the syntax stuff is completely arbitrary. We just spent like a week at work or more deciding between function pointer types for our Lua extensions, and it's such a stupid problem because there is like a bunch of languages that do it all differently. And how do you find the right one? How to find the best balance? And it's like, so I emphasize with him not wanting to spend too much time thinking about this. It's just some of the choices are slightly on, some of the choices are good. Anyway, so I like Jai in general. I think it hits a lot of the points that feel true to me. I just worry that it won't really go anywhere, and because of this, it's not going to be interesting for me personally. Just as today, there are other languages that might be nice, but they're so niche that, there's that, okay, so if you want to use Jai, but you can't use Jai for obvious reasons, there's this language called Odinlang, or Odin. The way this language was born is the author of this language was watching John's streams, and he was empowered. But this is the thing that John did really well, I think. I think one of the best things that will come out of Jai is kind of democratizing the idea of writing programming languages, which feels bad, but it's actually good, I think. Like basically what John did, I think, is that he said, well, language isn't anything special, we can just write one, and he did. And it takes time and it's hard, but empowering people is important, even if people fail to actually deliver as a kind of result of this, which is what usually happens. But like having people think, oh, this is actually awesome. I always wanted to do this, but I just lacked the motivation and certainty, and let me do that. It's fantastic. And so what happened is, and also John had a couple of really good syntax ideas. I really like this whole like data colon equal thing, and data colon int equal thing, and data colon is like a definition, and I kind of like this. After I saw this, I'm like, wow, this is such a good idea. I'm surprised I haven't really seen this elsewhere, but I feel like a language like this would be really easy for me to parse visually, and I would feel pretty happy typing this, right? So, so Odin takes some of the syntax from John's videos and some of the semantics from John's videos, and then builds a language around this, and then has a lot of different ideas, right? And this is open source, so what this thing does not have, and it has compile time execution, I think, and things like this. What this doesn't have is it doesn't have John's obsession over compile time. For example, it uses LLVM as its only backend, so if you compile it in debug, it's going to be substantially slower to compile than JAI. In release, it's probably close. And there's no, John is writing this big game and engine, not big, but like a game and an engine around his language, and I don't think this language has anything like this. But like, so if you just want a niche language to write code in and feel happy about this, there's a bunch of those, and here's one, right? You can try writing code in Zig. Zig is kind of interesting. I don't like it. Zig feels very alien for me syntax-wise, and I don't feel like it buys much with that syntax. So I feel like I would have been happier with Zig if it was more C-like, but that's just a weird syntactical personal preference. Anyway. Alright, how do you compare Clang, GCM, SVC toolchains as far as features and optimization? So, it used to be that Clang was this compiler that compiled code really fast. A couple of things happened since then. Clang got slower. GCC and Microsoft Visual C got faster. So in terms of the compilation throughput, I feel like the differences aren't substantial enough one way or the other these days. I've seen LLVM. I don't use GCC too much in production. I use it a lot just because it's the default compiler in my Linux shell. I probably I could have switched to Clang, I just didn't. I don't know why. So Clang, I've seen Clang a bit more often than Microsoft's compiler, at least, go into this like crazy. Here's really complicated code. It takes like 5 seconds, 10 seconds, 5 minutes to like generate code in release with optimization because some algorithm inside goes haywire. So, but generally speaking, right, I mean, compilation throughput is pretty comparable. At work, we are in an interesting situation where we have a code base that historically hasn't had really clean header kind of hygiene. We're working on fixing this, but it takes time. And because of this thing, we use precompiled headers. And so for us, Microsoft's compiler is way faster to compile code than Clang, because Clang's implementation of precompiled headers is just much worse in terms of compilation throughput. In terms of code generation quality, Clang is good. GCC tends to be pretty decent, although I don't use it as much, so I don't know. Clang is good. Microsoft's compiler used to be not great at this, generally speaking, but I've been pleasantly surprised lately with the progress that the Microsoft team is making on their compiler. Just as a random example, like, so I was writing the CMD kernels this week on stream. Microsoft compiler was slightly faster than Clang or GCC at executing those. Historically, Microsoft's compiler was really bad at optimizing CMD code, but they seem to have improved it sufficiently that in some of these cases where I'm just writing code, like it's better, right? So Clang is way ahead in general. GCC I don't know so much about. Clang in general is way ahead of Microsoft's compiler in terms of the C++ features and whatnot. So I guess it's good if you like C++ features. The really big thing that I like about Clang is that it's open source. There's two reasons why this is good. One is because of this it gains so much reach that it's now a de facto compilation stack in so many places. Because of this, there is so many eyes on the results of the code generation quality. Unfortunately, not compile times, but yes, results of code generation quality. So like Rust uses LLVM as the backend. If somebody is working on the Rust library and they find a problem in LLVM's optimization pass, they report this problem. Maybe they don't, but if they do, it gets fixed. And when it does, C++, Clang, right, C++ compiler benefits. Microsoft's compiler is more of a thing, kind of like some people use it, some people report bugs, sometimes it gets better, but it just doesn't have as much reach, right? And if there's a problem in an LLVM compiler, you can like try to figure out why it's happening, debug it, find a way to work around this. I've done this a couple of times with LLVM in the past, not with Clang, but I don't think it's particularly difficult. So it's kind of empowering to be able to like debug your compiler, profile your compiler, fix your compiler, like things like that, right? So that's nice. Although LLVM is kind of really heavy code base, so it's not very pleasant to work in. But yeah, I don't know. So okay, here's an example. just in more concrete terms, right? So there are some types of code. Well, like so, as I said, my CMD kernel for some reason run faster on MSVC. We actually had a problem at work with some of our CMD code with Microsoft's compiler because it didn't unroll one of the critical loops, and the Clang's compiler did. And in Microsoft's compiler, there's not even a way to control this. And in Clang, there is like a pragma. And so we ended up having to do some really crazy, unspeakable things to like force and roll the loop. And this brought the performance back to the level where it's roughly matching Clang. But so things like this, where Microsoft's compiler is stubbornly refusing to add some of the really valuable but non-standard code generation quality features, right, is unfortunate. For similar reasons, our Lua interpreter is noticeably faster, like double-digit percentages faster in Clang. I think it's basically, let's say something like 20% faster than Visual Studio 2019, and then something like 30% faster than Visual Studio 2017, at compiling the same code, right, like Clang versus. So Visual Studio keeps improving, but yeah. Visual Studio recently added address sanitizer, which makes it more like Clang had it forever, but so I don't know. I feel reasonably like if I had a choice of one. Let's put it this way: if I had a choice of one compiler, I would use Clang. Just no brainer. I would use Clang over Microsoft's Visual Studio compiler because it's open source, so I can fix things. It has wider reach, and it has more features in areas that I feel like are important. For example, it has built-in fuzzer support, which is invaluable. And there's like all sorts of benefits over this, right? And I would use it over GCC because A, it has more features. Again, like fuzzer, I don't think GCC has it. And also the code base in GCC, I just don't really like. Clang is way more disciplined, I guess, around their code and how it's written and how it's maintained and used, etc. Like GCC code tends to be really hard to read. LLVM code is not pleasant to read always, but GCC is like worse, I feel. And GCC has this weird licensing restrictions. Anyway, so if I had the choice of one compiler, I would use Clang. I feel happy. Right now, I am basically at work. We use two, Clang or Microsoft's compiler. I feel reasonably content with this. For us, MSVC is much faster to compile code, so because of precompiled headers. So maybe if that gets fixed, we can just massively migrate to Clang. I don't know. At home, I tend to use all three interchangeably, but I only use GCC because it's the default on Linux. Like if GCC was not the default on Linux, I wouldn't think about using it instead as a default. Whereas the converse is actually true. Like whenever I need fuzzing, I have to use Clang, things like that. So yeah, I don't like massive header-only C++ libraries. All my libraries are not header-only. Although one of my libraries has a header-only mode because some people like it enough that I just implemented this as like an option, but it's not the default. Yeah, somebody has this weird MapReduce example. The pain of supporting more APIs is terrible. So, if you're writing a school project, you don't need to support more than one API, right? Like if you're writing a school project, your goal isn't to write a production engine, right, or game. So for example, if you're writing a school project, you could say, oh, I'm only writing this on one platform, so I'm going to use the dominant API on that platform. If you're using Mac, it's really fortunate for you because Metal is a fantastic API to work with without any... Oh, I didn't talk about this at all, right? But Vulkan or DX12 are also not really pleasant, honestly, to use, like, without wrapping them. It's just, there's a lot of bureaucracy in some places. Like, it's not as easy to write code. So if you write a game or whatever, and you are content with that game only working on Mac or iOS and just you don't care, like it's a school project, just raw Metal is perfectly fine. You could use raw OpenGL and have the code technically be portable across more than one platform. but OpenGL has a lot of problems. You could use Vulkan. If you use Vulkan, you could, like, if I was doing a school project, I would ask myself what my goal is, like, why am I doing this? And depending on the goals, I could pick just one API, but which one depends on the context, right? Whew. What do top-notch graphics bros? I don't like the word bro, but you know, look at when hiring someone. I'm currently a student making a home engine. I feel years behind. Any tips? So I talked. The same question was asked, I think, when I was doing this chat thing last time. Oh, wow, it's been 2.5 hours already. So my general answer is there's not any one thing, and there is multiple axes that we evaluate people who come in. If you don't have an industry experience, it's a bit different, right? So if you have industry experience, we can talk about things you've done, the research or the production work that you've done, how interested was that, how deeply do you understand it, etc., how deeply do you understand GPUs. But like the scope of things that people could be good at changes when they don't have experience. They're like a college grad, right? For college grads, I haven't interviewed a college grad for graphics in a while, but when I did, I looked at a few things. One is, and they're kind of basic and amorphous, so I don't know if that'll help you a lot, but one is how many areas did you try to learn? So, did you try to look into different graphics APIs and what do they do? Did you try to look into various aspects of the various rendering algorithms, let me put it this way, and the theory behind them? So like, do you understand physical based rendering? Do you know what BRGF is? Do you know the word solid angle? What does that mean? Can you explain to me kind of the rendering equation and things like that, right? And did you look at practice of implementing these algorithms? So if you are implementing shadows, did you look at a bunch of different ways to do that? Are you reading presentations from GDC and SIGGRAPH around graphics? Are you able to show that you're actually interested in the research and happy to kind of follow along and try to deeply understand what it is and why it's important, right? Did you try to, like, do you have a concept of performance, right? The understanding of how performance works in graphics, what what are the common optimization techniques, how do you even evaluate performance, things like that. Did you try to understand how parts of the graphics pipeline work on a deep level? One question that I always used to ask people that who weren't super senior was to talk about MIP mapping. And that's a very deep question because there's so much in that. Like, do you know what MIP maps even are? How does the GPU pick one? How does the GPU sample one? How do you generate them? And then we can talk about anisotropic filtering and stuff like that. So in all of these, one other favorite question that I have is multi-sample anti-aliasing. Like, how does it work? Why is it useful? What's the pros, cons, stuff like that. So the point for all of these questions, though, is to measure. Somebody's saying these are easy questions. So the point of all of these questions is to measure the depth of each particular individual along that axis. Like, I don't like questions that just have an answer. Most of the questions that I was talking about, they don't have the answer. Like, you can't be like, oh, okay, cool, question X, find it somewhere, copy and paste like a line of text, say it, you're done. not really how that works, right? The way it works is I'm trying to understand how well do you understand that answer, and how many steps beyond this can you go, right? Because like when I started to talk about meep mapping, there is this long chain of like, okay, you understand this at this level, let me probe with a few more questions at the next level to figure out if you understand that, right? The best part about things like this is that usually it's kind of opaque for the person who is being asked the question whether they're doing a good job, because like I'm not even judging you. I mean, I will judge you later, but like I'm not telling you no, this is wrong, or well, sometimes I am, but like my goal is to figure out how much do you know and how much do you want to know, and whether you were curious enough to ask the questions. Like it's one thing to be like, okay, so I don't know if this is a good example. Like it's hard to think about these things in real time, but okay, so for example, you would ask some people about multi-sampling, and they would tell you that, there's like 4 samples and stuff like this. And then you would ask how this is different from super sampling. And they would just be like, I'm not sure, or I don't know what super sampling is. And that makes it clear that you didn't really try to understand the topic. You just saw, oh, graphics cards support this technology that's called multi-sampling. Let me like read a paragraph of text about how it works, and that's it. This is not deep understanding. Deep understanding is, what's the problem that's being solved? What are other ways that can solve this problem? Why are they bad? Why is this better, and how is it worse? And then, there's like 15 other questions that you can ask. So anyway, so my advice would be, try to read a bunch of papers, try to implement a bunch of papers, try to just implement a bunch of rendering algorithms, then try to optimize a bunch of rendering algorithms. Try to use graphics. One very useful exercise is go through render doc, through a graphics frame, and then just ask yourself, like, do I understand what this stage does, and do I understand what each of the kind of properties of the stage, like scissor, rectangle, whatever, what they do? Then do I understand kind of why I might use each one? What's the rendering algorithm where each one is useful? And just doing that exercise will kind of leave you with a deeper understanding generally of graphics pipeline than what you might get by just like reading a documentation article about this. Yeah, I don't know what else to say about this. Like it's complicated. I don't really know. It's hard to. So the way I did all of this is I just wrote a lot of code, right? I was like, oh, shadows are so interesting. Let me read a bunch of papers. Let me try to implement a bunch of papers. Let me like try to measure performance and compare it and try to figure out if I can make it faster. And let me ask like stupid questions on graphics forums, and then have other people help me and stuff like that, right? So I feel like you have to go through this process. So there's not really a checklist, right? Where it's like, okay, I did this, I must be a graphics developer. But I think the process is read papers, read articles, try to write code, try to implement code, try to debug code, and try to understand how graphics hardware works and things like that. What's the most difficult technical problem you had to handle during last week? Last week. Let's assume this week. It's an interesting question. I feel like the answer for last week was I was doing a bunch of experimentation on like compression stuff, and I had to try a lot of different ideas about encoding and like look at the distribution of bytes in various places, like look at a lot of stats basically around the data and kind of try to figure out what's the balance between the performance and like implementation complexity and stuff like this. These things are generally challenging for me because it's one thing to know what you want to do and just to write code for this. Like this doesn't seem to be that hard for me. But that thing is probably hard. I'm not actually sure what was the hardest thing this week, because the other hard thing that I was doing last week actually was it's not a very complicated problem necessarily, but I was trying to write, it turned out to be a bad idea, but I was writing a static analysis pass to find undefined variables or uninitialized variables, or like conditionally uninitialized variables, like cases where not all paths through the code lead to a variable being initialized before it's used. And it's really, really tricky because you have to very precisely follow the control flow of the program. So it's like a graph traversal of the control flow graph. But I didn't want to build a control flow graph because it takes time. And I try to have the code be really efficient in terms of the control flow graph complexity and the number of variables and all of these things. And there is a frustrating amount of work that you need to do to actually answer the question, like, is this variable initialized or not before it's used? Because the context that I'm solving this problem is slightly different from C++ or whatever. Like, so this was for Lua, but you can imagine in JavaScript or any other language, like it's fine to ask if the variable is defined or not, but it is not fine to add it to a different variable. And so you have to figure out what even the rules are, because it's like fine to check the variable, but it's not fine to do other things with this. And if you have a conditional expression, like if you have something in C++, like this is probably the hardest thing that I've done. I've done like CMD stuff and optimization stuff, but a lot of the stuff is just naturally, it's like, okay, sure, you just do this. You look like it doesn't seem as hard anymore. So if you have an expression, a simple expression like A and A arrow B, right? So this is okay, because like in C++ context, imagine you're writing an analysis pass that asks, is there a null pointer to reference in my program? So in this case, the answer is no. But to know that the answer is no in this case, you have to track during the semantical analysis of an expression, you have to find kind of branches of this expression where some precondition is true, or if you have not A or A arrow B, this is also fine, right? But if you have like not A and, this is not fine. And so there's a lot of nuance in this where you have to track all of these like conditions, and then you have to correctly update them and, you know, like invalidate them. And then it's like, okay, then if you say, I told people there was not going to be any keyboard sounds on the stream, but I guess I was lying. So here's like a basic example, right? And this is going to be really primitive, but just to illustrate the point. So like in this case, after the if condition else, we know that A is not null. But during evaluation of every branch, there's actually like a point before and after, like here it's null and here it's not null. And once the whole block ends, we know it's not null. But if you have something like this, well, something like this, then we don't know that it's not null. So it might be null at the end of the whole block. And you're trying to do all of this pretty quickly because you don't want to slow down the general semantic analysis of the program much. So yeah, this is probably actually the hardest thing I've done in the last couple of weeks. It ended up not being useful because it ended up being the case that these preconditions become excruciatingly hard to track if your goal is like almost no zero positives or false positives, and I didn't quite get to this stage, and I'm not sure I really want to get to the stage, so I kind of put this on the back burner. But yeah, this was hard, this was challenging. Bum, 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 bum. Thoughts on development on Linux. So we're gonna spend 20 more minutes on this, and then I guess maybe more, we'll see. But it's like third hour of doing this. Thoughts on development on Linux. Yeah, okay, for the last couple of years I have been using a setup where I have Windows, but I use Windows subsystem for Linux, it's called. This is that, which runs almost, it doesn't run a Linux kernel, although Microsoft is going to change. This is like the biggest thing that I'm excited about in the upcoming Windows 10 release. It's rare that you get excited about any Windows feature ever these days, or any operating system feature ever these days, but I'm really happy they are doing improvements in that thing, and this thing, like, I really like that. So yeah, this is like a Linux, so right now this is a Linux shell that's running on top of an emulated Linux kernel. That is not the real Linux kernel, but all of the system calls from this shell right now go into the Windows kernel through this emulation layer. And I feel like almost everything that I do, not everything, I spend like half the time now in this kind of environment where I'm sort of using Linux, but I'm not actually on Linux. And I really like this because every time I use Linux, I run into the stupid problems. Like, oh, you want to play a game, tough luck, the game doesn't run on this, or the game hasn't been ported, or whatever. Oh, like you plugged, like I don't know, like my Wi-Fi doesn't work, or my sound's glitching, or you plug the new monitor and your monitor doesn't work, or you plug the 4K monitor and you need to change the DPI scale settings, and none of the programs that you have support this in any way, shape, or form, or So I just never felt like I'm happy when I'm using Linux, and I feel like I'm happy when I'm using Windows, but using a Linux environment for development, right? I also use Visual Studio, to be clear, so I use a combination, right? And this flexibility is really valuable to me. I kind of got into the mode of liking this when I used Mac a few years ago, where I disliked some parts of the Mac experience, but what I really liked was the presence of a robust Unix terminal and Unix shell and Unix programs, and a lot of things just work. And here I can do, I can do find, I can do grep, I can do whatever. So, but yeah, I haven't really seriously used Linux for a while now. I used to, like 15 years ago or so, like maybe slightly more, I was an avid Linux fan. I was like, you guys know nothing, you must use Linux. Most challenging problem for multi-threaded Lua currently, just very briefly, I don't want to talk too much about this, but the biggest problem is just we want to make it possible for scripts to read objects that other scripts might be writing to, because not allowing this at all is a bit too fragile from the logic perspective. Like you're doing a raycast and the raycast returned you a part, and I want to know what the part position is, and what happens if somebody else is changing that part's position right now. So we kind of really want to allow this, and there's two different ways how this can work, and I'm currently trying to figure out, so this is the most challenging part that I've done this week, actually, is trying to do design for this multi-threaded execution that's compatible with our worlds, that's relatively compatible with how developers write code, but that is robust so that we can actually support this in engine. I don't have an answer for this yet, but yeah, that's been hard. Jai, syntax not feeling good. Functional programming languages. So the word functional programming languages gets harder and harder to understand over time. Is C++ functional? Well, C++ pretends like it has first-class function objects. They're not really function objects. They're kind of different from other things, but it certainly supports some functional programming paradigms. So some people may say, yeah, C++ is like a multi-paradigm language and one of them is a functional one. Somebody else would be like, what are you even talking about? C++ is a horrible mess. Like, it's not what a functional programming language looks like. Then you can ask, well, is Scheme a functional programming language? Or is OCaml a functional programming language? And you may say, yeah, well, of course, definitely it is. But some people will say, well, in both of these, especially in Scheme, but also in OCaml, there is really no purity in computation. You just mutate things left and right, and this is just not really what functional programming language is. So really, functional programming languages are Haskell. So I don't know what this word means. Or I don't know what you're asking, and I don't know what your internal classification is, right? So in general, I like some of the ideas of the functional programming languages, but I don't ascribe to some other ideas. For example, in some programming languages, like, people tend to treat mutability as this crazy, horrible thing that happens. And I think what a lot of them miss is that the problem with the mutable state is the scope of the mutable state, not the mutability itself. Or mutability is a problem, but like the reason why it's a problem is the large scope of the state. So for example, if you have a function that sorts an array, there is this quick sort in Haskell, like what is sometimes shown in Haskell tutorials. Let me see if cool. So this is the quick sort in Haskell. Oh, so this is a good tutorial because it says slow quicksort, which is kind of an oxymoron. But so, here's a beautiful algorithm that does a quicksort in like 4 lines of code. Isn't that cool? Well, this is cool. The problem is the complexity of this algorithm is, I don't know Haskell enough to be able to like just on the spot be like, oh yeah, the complexity of this algorithm is like not n log n in the average case or whatever. The memory complexity is definitely not n log n. Is plus plus? No, I guess this would be linear. So barring weird thunk allocation stuff, maybe the complexity of this is fine, but the memory complexity of this is not fine. And this runs orders of magnitude worse than an actual quicksort does. And so I feel like this is a general class. And in this case, the example without mutability is actually really easy to understand. But there are other cases where the mutable code is really easy to follow, and the code that doesn't mutate data is really hard to follow. And so I feel like people throw, what's the expression, like people throw the baby out with the bathwater a bit. In some, again, like if you take this too far, it's not good for you. But in general, so I spent several years of my life writing a lot of F# code. In fact, this cup that I'm drinking tea with from, it's an old cup, but I don't know if the camera shows this at all, but there's a GitHub URL and a GitHub hash here, and my GitHub username, and this is, it's very, I was super happy about this. So I contributed an optimization to an F# compiler that it was a while back, I don't even remember, 5 years ago. What the optimization did is it eliminated allocations in some common patterns in F# when you use tuples. I won't go into what this means, but like whatever. And I think the way it happened is before F# became open source, I filed a Microsoft Connect bug being like, hey guys, your compiler allocates stuff here. It's not really very good. Oh, the compiler was source available. So I filed a bug saying the compiler doesn't do a good job here. I tried to fix it myself, and here's a patch. But because you guys don't actually have an open source repository, the best I can do is just attach this patch to the ticket. And that went nowhere, but then when F# became actually open source, somebody commented on this ticket being like, oh, do you mind actually submitting this to the F# repository? Maybe we should find this just for fun. I don't know if we can find the actual F#. I don't even know where. Is this the old repository URL? This might be the old repository URL. I don't know if we can find the commits because I don't know. But we should be able to, right? How do I do this? Do I just find myself in this repository? Aha! So yeah, so in 2015... Oh, I think somebody took my... Oh, yeah. I think somebody took my issue and took my patch that I attached to this issue. And this is the actual patch, like it's not a whole lot of code. And then they created a ticket, a PR for this, and they were like, hey, it's kind of your code, like, do you want, yeah, somebody said, can we find the original author? And I was like, sure, I'm happy to do this. And then I had to write unit tests and stuff like this. And this got merged into F#. Oh. I didn't even see that. I guess I was supposed to post my photo to this. Oh, they took my GitHub profile. Cool. Anyway, this thing happened, and then Microsoft sent me a cup, and it's awesome. And this cup, you can tell it's a really old cup because, you know, maybe I haven't been taking very good care of this. It has this beautiful pun on the front, which is a cup generic that you instantiate with $T. And in F# and ML languages, the way you read this is cup of, and then the argument name, which is T here. So you read this as cup of T. Like in the language, like if you had a dictionary of a dictionary that mapped int to string, you would say dictionary of int and string. I forget what happens if you have two arguments. Anyway, why did I go here? Oh yes, so writing F# code was good for me. I think it made me a better programmer, for sure. And I think it clarified a lot of my thinking about algorithm design. However, I don't apply a lot of the techniques. So it clarified my thinking, and I feel like I can reason about many things way better. F# taught me a lot about some part of the programming language design that I was not familiar with. It taught me a lot about kind of the joy of pattern matching and these high-level constructs and the type inference and the pros and cons that come with deep type inference, like global type inference, how people call this, that goes kind of bidirectionally throughout your program and just infers types left and right and stuff like that. So it taught me a lot of things. I suspect that I wouldn't be able to write some of the code that I can happily easily write today without like that experience, but I don't actually write F# code anymore. I haven't done this for a number of years now, and it's not the case that I write C++ code today as if it's F# just C++. So it's not quite like this. But which is to say, if you haven't ever used a functional programming language, You really should. It expands your horizons. Do functional languages, are they critical for you to be able to do work? I don't think so, and then it depends on what type of the functional programming language you're really talking about. Anyway. Distant future of programming. Program memory, writing it in text. So I'm not really an expert on this. I think this goes a bit into the kind of cognition and this kind of high-level metaphorical concepts, and I haven't studied this a lot. I don't really know this space too well. However, I think it's kind of telling that for years and years and years, we continue to write programs as text, with one exception, with one dominant exception, which is blueprints and shader graphs and that kind of like visual programming stuff. But the thing with visual programming is it's not actually good at writing complex things. Or it's not good at all at making complex things easier. What it is good at is it's good at getting people for whom it's hard to write text programs, let's put it this way. Not because like they don't know how to type or whatever, but just because their mind doesn't work the same way. So what it's good at is at allowing people with this mental model to be able to do things they weren't able to do before. I don't think it's the case that in any existing visual programming paradigm, you can implement, most of the code that I'm writing day to day in less time, less space, less mental effort, etc., etc., etc. Maybe this is true, but I just see no proof whatsoever this is the case. What I think is the case is that there are people for whom the concept of a variable name, I've spent a brief, I want to say a year or so, maybe half a year, teaching. When I was in high school, I was teaching programming to middle schoolers. For many people, the concept of a variable, and I mean this goes back into the math, like math has similar problems, but in programming they're just way worse, or a concept of a loop or things like this, like for many people it's just so very difficult to understand that. And it's not because they're stupid, it's because their minds are wired differently. Like, I cannot do art, and it's fine. Like, it's not because I'm inept or whatever, it's just my brain doesn't work this way. So I feel like for these people, I feel like this is why visual programming took off in some of these areas, where for some people it's just hard to like reason about non-visual things, and so they go to the visual things, right? But I don't think it's actually effective at doing professional programming, right? Like where you're trying to build really deep, complicated systems. And so then the answer would be, well, if you're asking about, and even if you're talking about reach, like there are people who think that everybody should be programming, and I'm not really sure why, honestly. There's this whole concept of programming as a basic skill. So I don't think we will go away from text really, at least definitely not into visual programming. I don't think syntax and typing is really the problem. Like, I think people for whom it's hard to use, JavaScript or Lua or whatever, like I'm not even talking C++, right? Like, it's not about typing. It's not typing that's the problem. Like, emphatically, typing is not the problem when you're writing C++ code or Rust code. Like no. Visual programming will do nothing to help here. So the answer is really I don't know. One thing that is emerging though, it has been emerging for the last many years, is the approach to problem solving where instead of solving the problem, you teach the computer to do this, right? This whole neural network, machine learning stuff. And that's kind of interesting because you're not actually writing code, or you are writing code, but the code that you're writing is very, very different. You're writing way more code that tries to understand the data that you have. You're writing code that tries to guide the computer into trying to be able to reason about this data. And the process of writing, debugging, tuning that code, to my knowledge, I'm not an expert, but I have friends who are, I've talked to them about this. The process is like substantially different than the process of writing C++, right? And I don't think this is the answer, but I think this is a segment that has been really weak for years and will be pretty strong for years. Like, I think there's going to be a whole class of engineers who are machine learning engineers where your job isn't to write a program. Your job is to study the problem enough to understand how to best coerce the computer into generating a solution for that problem. And you see this happening today, right? Like, absolutely, this is what's happening with machine learning today. Now, it's relatively new. The set of tools that we have today for this kind of stuff, right? They're all relatively fresh. Like, I don't know. So nobody likes TensorFlow from what I know, but TensorFlow was released 5 years ago. C++, I don't even know. 77, I want to say. When was this? 35 years ago, 85. The language I think is older, but it's probably the standardization date. So it's really, really early. So I think the tools will change a lot. But I think this is a class of programming that we will see a lot that we don't have right now. But it's important to understand it's not just asking. It doesn't mean like I don't understand the problem, so I'm going to ask the computer to solve this. Some people do this, but it's not actually how you get good results. It's a different way to understand the problem and a different way to solve the problem, where you don't actually see the path to solving the problem clearly, but you identify all of the pieces that are important enough for the machine to be able to do the rest. And I don't really know enough about this to talk about this more, right? It's just, I'm not an expert in this. But yeah, so this, if anything, I think this will be, but it's not really about visual programming, right? Like, it's not about text versus visual at all. It's really a different way of thinking about the problem. And then we still probably will use text to actually, write the code to generate these networks and write the code to analyze this data and all of this stuff. Maybe one day we will stop using text, but I just don't see text as being the big problem. I think the difference is more meta. Oh, all right. Is it a My Anime list tab pinned in the top left? Yes. I like anime. I started. I'm gonna tell. Sorry, I skipped the question. Any interview question for a super senior developer? So, okay, like as I said, really, right? So when I interview people, it's really hard for you to tell if you're doing well or not. Because when I interview senior people, what I talk to them about is, and I can just say this up front, like it's not a secret or anything, 90% of the information that I get, and you actually can watch, I think Casey Muratori did a video about this, where he did mock interviews like this. I talk to people about the things they've done. That's it. That's really it. But I get a ton of information from this. I talk to people about things they've done, and I try to understand how did they come to the solution that they came to. Do they understand the solution at every level really well? or did they just like copy something somebody else did without thinking? Did they explore alternate paths, and how many and how, etc.? Did they strive for excellence in their implementation? Like, not like, oh yeah, I'm just gonna write this thing, it's gonna be slightly kludgy, whatever, I'm just gonna get it done. Like, no, like, were they like, I'm gonna write the best thing in the world, and knowing that you might fail because it's really hard to do something that's the best in the world. I don't know that I've done anything that's the best thing in the world. I don't know. I don't know. I have a pretty good XML parser. Whatever. I don't know. But like, it's really hard to do something that nobody else has done. But I think you have to approach the problems as, I'm just gonna do my best, and I'm just gonna go way beyond, and I'm just gonna see what happens. And so, and there's like many more dimensions, right? And so I'm just gonna talk to you about things we've done, and you will not necessarily know if you've done poorly or well, and I'm just gonna use the collected information, right, to understand how likely it is that you're gonna excel at solving problems that you know about, and problems that you don't know about, and problems that we don't know about. If you want more details, jobs@roblox.com. Feel free to apply. Say you are watching Arsenius stream and were really curious about this. Right, so anime. Yes, I started watching anime a few years ago, a number of years ago actually. I remember how it happened. I don't remember when it was. It's kind of curious. And I can tell the story because it's interesting. So it's weird. I don't know, maybe this is common, but so the whole concept of anime was strange to me. I didn't really know. I knew it existed. I didn't really watch it. It felt like Sailor Moon to me, where there's this like stupid girls show. Sorry if any girls are watching, but like Sailor Moon is not my thing. Um, Especially it's probably not very appropriate for my age because it's probably for like 15-year-old girls or whatever. So it just felt like this weird thing that I don't understand, right? And I used to watch cartoons in my childhood, right? But I didn't keep doing that really. I feel like there's this big gap in my cartoon watching where I watched a lot of cartoons before I was like 10 or whatever, and then I watched no cartoons for like 10, 15 years, 10 years or more, yeah. And then I've actually watched a few cartoons, a few cartoon series and stuff. Like, I don't know, I watched the entire Teenage Mutant Ninja Turtles series like 7 years ago, I want to say, and the entire Batman cartoon around the same time, and I just loved it. It was awesome, and it feels weird, but like whatever. I'm not ashamed to admit. Okay. But I think the thing that got me into cartoons maybe was Futurama, not anime. But anyway. But, I was watching movies occasionally, obviously, and stuff like this, and I watched Kill Bill. Kill Bill, I think the first Kill Bill. And the first Kill Bill has this scene. I'm not gonna, like, find it, but, you can Google it. First Kill Bill is it's like a... So there are people who like really deep, intricate plots and stuff like this over anything else, and I really like that. But I also really like just like... Maybe the plot is kind of mundane and it's like, whatever. Obviously, you know exactly what's gonna happen, but there's just free-flowing action and beautiful camera work and amazing, character design, for lack of the better word, and things like this, and I've always appreciated that. So like, I'm not a person who would not watch a movie just because the plot is like not very interesting, right? And the plot in Kill Bill is, it's it doesn't feel like there's anything really interesting about this, honestly. But I really liked that movie. It was one of my favorite movies at the time, which probably doesn't tell a lot of good things about me as a kind of movie connoisseur. But There's a sequence in Kill Bill 1, which I'll spoil for people because this movie must be like 20 years old or something at this point, where the girl hides. I just vividly remember this, right? This is like strong childhood impressions for you. So there's the girl, which is the protagonist, right? Which is like Uma Thurman, I guess. She's hiding under the bed as the Yakuza comes in and murders her parents. Her mom, I guess. And she's hiding, and for some reason, I don't know why, it's not an anime movie, right? But there is this one sequence there which is anime. And now that I've seen enough anime, I know that it's very westernized. Like, it's not actually how anime looks exactly, but it's fine. It's close enough, right? So she hides under the bed, and there's the Yakuza who storms in and is like, I guess he's being owed money or whatever, and he grabs the katana from his henchman and like stabs the mother, who is, I think, on the bed, and the katana goes through the bed and goes right past the daughter's eye. And this is the only, there is like 5 minutes of this or something in the whole movie, and I was like, oh wow, this is like the best sequence of that movie. It somehow captivated me. And yeah, so then I kind of started watching anime, and now I've kind of watched a lot of anime. So now I basically don't watch movies. I forgot when I feel like I watch basically 1-2 movies a year, and I watch a lot of anime. Not a lot, but like I watch a few hours of anime a week, I would say. All right. How do you find these resources such as articles and stuff? Reputable sources. No easy answer. So in general, I would recommend just following, first follow just GDC, SIGGRAPH, things like that, just follow the presentations. But, and in, I don't know, there's blogs and things like this, but today, this question is actually easy to answer. So today, I think what you do is you subscribe to Gendrik Ilner's blog, where he does this graphics programming weekly series. And this is basically the things around graphics that are sort of interesting that happened. Not all of this content is top-notch. However, my advice would be that you start by basically this is enough of a resource. Everything that's interesting is likely going to be here, so you're not going to miss anything really big. Some of these things might not be very interesting for you, so my recommendation would just be every week just look through this, and if something captures your attention or seems like something you don't understand especially, just read it. And that's honestly, I feel like this is a fantastic resource. This did not exist when I was kind of growing up and stuff, but when I was growing up, we had a good community in my my native language and stuff like that around game development and graphics. So this is how I learned a lot of stuff. Not how, but this is, I guess, what motivated me to learn a lot of stuff. Anyway, so I think this should be your source for graphics material. You don't have to read every single article, right? Like, read the things that seem interesting to you or seem confusing to you. The reason why it's important to read things that are confusing to you is because you might not know that something is interesting before you kind of know about it, right? And so it's important to try to push your boundaries, stretch your boundaries, and push yourself to kind of, I've only ever done, here's, we just talked about the Unity stuff, right? So, hey, Unity Toy Path Tracer. Maybe this leads you to trying to understand what this whole data-oriented design is all about, and that's valuable. All right. We're really close to the end, so I'm just gonna go through the rest. Keyboard SMR, how's the LED going? Not sure what the LED question is about, so I guess I'm not gonna answer that. Some chatter around stuff. Arkansas computer coding. Yeah, I don't get this. And I feel the reason why I don't get... Okay, here's the reason why I don't get this. If I keep going on tangents, we'll never finish this, but... My mother is a teacher, is a math teacher. She has been a teacher for years now, and she still is. She still works. She still works now. She's not in US. She's in Russia, but Russia is on quarantine right now as well. So it's not. It's kind of stressful for her to figure out all of this tech stuff. But so she's a math teacher, and she's a math teacher in middle and high school, right? So she works with lots of kids, and she sees like tons of people with very different background. And I don't feel like I appreciated the just how different people are. For me, I'm like a math person, sort of. I don't actually do deep math, and I don't know if I'm good at doing deep math, but I've spent years doing like lots of math stuff. And before I went into programming, I didn't know what I would do with my life, but it was clear that it would involve math in some way, shape or form. And it just came natural to me, right? So I'm not like, I shudder at the, here's a math paper where the abstract is like indecipherable. I am not like a good person to read that stuff, but I don't feel it's my fault as much as I feel like that community is just not emphasizing the understanding of these concepts outside of that, whatever. But point is, it always made sense to me, right? And this is why I think programming is my passion, because it makes so much sense to me and it's so interesting and stuff. And it's natural to think, well, shouldn't everybody be like me, right? But like the fact is, no, everybody is not like you. And there are so many people who I know that it's so hard for them to get into math, but it's so easy for them. So I've always struggled with history. I can never remember dates or events for the life of me. Like, you would be amazed if you try to have a conversation with me about the history of my home country. I remember blimps, right? You would be amazed at how little I know. I knew way more when I was learning this, but now it's all completely gone. And even when I was learning, it was so hard to just remember the sequence of events and to try to kind of, it's like, who was the wife of like the third emperor? Third emperor? What are you talking? I don't know. And so many people I know, it's just so, it comes natural to them. And I know so many people for whom it's so natural to do art of so many different kinds. And they do sculpting and they do painting, and I kind of studied all of this stuff. And if you look at my paintings, they're really sad. I mean, you looked at my handwriting and it's not particularly pretty. My handwriting is actually better slightly usually, but my tablet is at a weird incline and stuff like that. And so I don't quite see why programming is different. Like, it's such a weird special... Okay, so like everybody should learn math enough to be able to add and multiply and understand percentages and stuff like this. And like understanding exponents turns out is really important in this whole situation. But I don't think everybody should learn how to differentiate functions and what an integral is, and like enough graph theory to be dangerous, and what's like a... I don't know some of these terms in English. Not dual. Bipolar graph? I'm not sure. What's like what's even a matrix, right? Like, you don't need this. So why would programming at the basic level is so much harder than just arithmetics? Why would this be... Like, I guess it just depends on how deep you go. Like, maybe everybody probably should be taught basic programming in school, but it's the same as math to me, where like, you're not teaching this for people to apply the skills so much as you're teaching them to try to figure out if this is their passion and strength, and if it is, they go deep, and if it's not, they stop. Anyway, the book Zen of Assembly Language is very good at explaining how simple algorithms eat CPU cycles. I think it relies on compilers more than on program structures, harmful for performance. I mean, I don't disagree with this. I think it's important. Compiler is a tool. In general, it's important to be able to understand what your tools do, to understand where they fail and where they succeed, and to use them in situations where it makes sense. But don't expect your tools to be magic. And so I think this is the approach you should take to compilers. You should not be surprised when okay, so the correct way to use an optimizing compiler is not to write slow code and hope that compiler will fix it. It's to know exactly what compiler is likely to optimize and what it's not, validate this hypothesis, and write your code accordingly and adjust according to the behavior that you see, right? So when I write loops in C++, I don't expect the compiler to vectorize them. I'm surprised when it does. And people tell me how occasionally, well, it doesn't often happen because I don't talk to these people, but I sometimes see conversations on the internet where it's like, yeah, no, you should, like, the compiler should do it for you. And then, last week, 3 compilers, top of the line compiler, four functions, data parallel code written in C++. 3 compilers, 4 functions. 1 function is vectorized by all of them. Great. Is that true? No, I think one of the compilers didn't. No, one function is vectorized by 2 of them, I think. And the other one you can coerce into doing that by enabling a compiler flag that is disabled by default. And the other 3 functions are just blank, like not a single one of these. And then it takes me mechanical I'm doing mechanical transformations to make it run, right? So you shouldn't assume that magic is happening, but you should know what exactly compiler does do and does not do, and use it accordingly. All right, futures by GitHub, just keeping that, like it will, the repository is not going to get updated at this point. We're just going to ship this on production this year. And I don't think we are doing the sandbox thing in general. Like, we are doing internal experiments, but there's no promise that any internal experiments result in external demos. We did this with the Avatar Evolution build last year, and end of last year. So occasionally we will do these kind of like aspirational separate releases where maybe some of the stuff gets shipped to production, who knows when, but it won't happen super often. I think the existing GitHub will just be defunct. Link animal list, it's Zuxig on my animal list. It will not be very, I'm not an anime connoisseur, like I'm not, I watch things that are slightly stupid, and as I said, like, okay, basically my taste ends up being kind of mainstream, as I found. Generally speaking, my anime rating correlates with my opinion of the anime to an extent. It's not always the case, like it depends, like sometimes something would be rated like 7.5 and I would be like, I don't really understand why, I'm kind of bored of this. And sometimes something would be like 6 and I'm like, oh yeah, this is cool. So, but yeah, I think it's Zuxig on my anime list. So English is not my native language. Envy people who were born native speakers. So, English is not my native language either. My 2 pieces of advice are, one, learn English. Sounds like you have already done so. The other one is find a community of people who speak your native language and share your passion, right? This helped a lot for me, right? Like I only really started being decent at talking in English uh, probably 10 years ago, less than 10 years, I don't know. My accent was super horrible 10 years ago, that I do know for a fact. It's probably not great today, but I don't really care. My accent, my accent sounds completely normal to me. I think it's probably normal, but it sounds really, it doesn't sound super great. Probably, but yeah, my accent 10 years ago was really bad, but like my ability to also maintain conversation wasn't super good 10 years ago. But 10 years ago, I already was working as a professional graphics programmer. And I read a lot of English and I wrote some English. So I think it's like reading first and writing then speaking, right? So anyway, find a community that speaks your language. This helps a lot usually, but also in programming in general, probably in technology in general, definitely in programming, the better you know English. Like, there are people who, when I was growing up, there was this community that spoke my language, and there were people there who would not read something that's published in English. They would wait for a translation, and that I felt really hampers your education. And the next thing that hampers the lack of language, that's hampered by the lack of language skills, is that once you understand what is being written, you have to understand how to write. Because if you don't write anything in English, people will not know about you, and this will hamper your career. And then you can learn how to speak. So yeah, like absolutely learn English. You have to be comfortable. The first thing, you have to be comfortable reading technical documentation, articles, etc. The second thing is you have to be comfortable writing about technology. After this, it's fine. If it's hard for you to talk to people, it's actually okay, sort of. It just gets one job or one, like go somewhere. Hold on. Oh yeah, you moved to Ireland for half a year, right? So you know how it goes. But yeah, like English, super important. Like if you don't know English, it's too early to learn C++, in my opinion. Alright, did I ever use C for graphics by NVIDIA? Yeah, totally. I started with CG when I was doing shaders. CG is basically dead now, but a lot of this ended up in HLSL, so to an extent I still write C for graphics. Occasionally, I don't write a lot of shaders anymore. Right, foreign language chatter, think in English. Yes, I started thinking in English a lot. So I've been in America for almost 8 years now, and I've been in Canada for a bit more than a year before that. I feel like I've started thinking in English more and more frequently in the last 3 to 4 years, I want to say. All right, I went through the list of questions. So, the best thing to do in this situation is to end the stream before anybody gets the chance to to ask one more question, because clearly this could keep going 4 hours. I didn't actually expect that it would be 3.5 hours, but it's fine. Obviously, in this situation, like the capacity for human contact is limited, so that's a good replacement. All right, thank you everyone for sticking with, especially people who have been here for like 3.5 hours, which I don't know how many people are, but thank you everyone for being on the stream. It was fun, and I feel we talked about a lot of kind of we've talked about a wide range of topics, from graphics and programming languages and performance and mesh optimizer algorithms and, anime, and God, no, we haven't really talked about anime. Okay, if you want to talk about anime, in my opinion, the best anime from the last season, from the season that have just ended, is the refresh, or rather, it's not even a refresh, they just aired it again, of ReZero. ReZero is a fantastic anime. I think it came out like a couple of years ago. I just the first episode, first season. It was awesome then, and I kind of forgot how good it was up until they re-aired it this season, and I watched it again, and it was super good. And there was supposed to be a second one next season, like now, but of course, maybe because of the pandemic or maybe because of something else, I think they moved it to later in the year. So that's unfortunate. But ReZero was awesome. I think this is the basically in the last few months, the one that I most enjoyed was clearly ReZero. Anyway, all right, thank you everyone, and maybe we'll do it at some point again. We will see. Let's end this. We will end this exactly in 20 seconds because the YouTube counter says that it's been 3 hours, 29 minutes, and 45, 46 something. I don't know if I'll have to press the confirmation button. But let's just say I won't. All right.